Imagine for a moment that something has shifted. Not dramatically, not with any kind of announcement. No cracking of the earth, no sudden roar from the sky. Just a quiet, almost imperceptible change. The kind that takes centuries to confirm, the kind that no single human life would ever be long enough to fully witness. The oceans, those vast and ancient bodies of water that have covered most of this planet for billions of years, have begun, very slowly, to leave. Not all at once. Not even noticeably, really. Just a little more than before. A little more each decade, each century, each millennium. The water is going, and the world has no idea yet. If you were alive at the very beginning of this process, you almost certainly wouldn't know anything unusual was happening. And honestly, neither would your children, or their children. The first generations of humans to live through the early stages of this change would go about their lives in more or less the same way people always have. Swimming in the sea, fishing, sailing, watching storms roll in off the water. The oceans would look the same. They would smell the same. The tides would still come in and go out just like always. There would be no sign, at least not one visible to the naked eye or felt in the body, that anything had changed at all. That's one of the stranger parts of this whole idea, that something as enormous as the slow disappearance of Earth's oceans could begin so quietly that the people living through the beginning of it would have absolutely no sense that they were standing at the start of one of the most profound transformations in the history of the planet. And when you think about the sheer scale of what the oceans actually are, that makes a lot of sense. The oceans hold about 1.3 billion cubic kilometers of water. That number is almost meaningless when you hear it, because our brains aren't really built to hold figures that large in any useful way. But try to sit with it for a second. 1 cubic kilometer of water is already a staggering amount, roughly 264 billion gallons. Now multiply that by 1.3 billion. The oceans aren't just big. They are almost incomprehensibly massive. They cover about 71% of the planet's surface. They reach, at their deepest point, nearly 11 kilometers straight down. They contain somewhere around 97% of all the water on Earth. So even if a significant amount of water were escaping into space every single day, enough to fill lakes, enough to flood cities, it would still take millions of years, possibly hundreds of millions of years, before the oceans were actually gone. The scale of what would need to happen is so far beyond what we naturally picture that the early stages of this process would look, to anyone watching, like absolutely nothing at all. In a way, that's almost more unsettling than a dramatic catastrophe. A sudden disaster has a beginning, a moment of rupture. This would just be a slow, patient unraveling. One that would outlast every civilization, every language, every memory of the world as it once was. Now, here's the thing, Earth is already doing something like this, just at a rate so slow it barely registers. Right now, today, hydrogen is leaking off the top of our atmosphere and drifting into space. It has been happening for as long as Earth has had an atmosphere. It's not a crisis. It's not even a concern, really. It's just a fact about the planet, the way a very slow leak from a tire isn't a problem until enough time passes for it to matter. Water, as you probably know, is made of hydrogen and oxygen, 2 hydrogen atoms bonded to 1 oxygen atom. When water molecules make their way high enough into the upper atmosphere, some of them get broken apart by the energy of the sun, and the hydrogen that's released is light enough that it can escape Earth's gravity entirely and just drift off. Gone. The oxygen tends to stay behind, but the hydrogen leaves, and since you need hydrogen to have water, every hydrogen atom that escapes is, in a very small way, a tiny piece of the ocean that will never come back. At current rates, this process is so slow that it's negligible over any human timescale. Earth has been losing hydrogen this way for billions of years, and the oceans are still here, enormous and full. But in this scenario we're exploring, something has changed. The rate has increased, the balance has tipped, and over a long enough stretch of time, that slow leak becomes something much more significant. It would start in the warmest places first. The tropical seas, those sun-drenched stretches of ocean near the equator, brilliant blue and warm to the touch, would be the first to feel the difference. Heat drives evaporation. The warmer the water, the more easily molecules at the surface gain enough energy to break free and become vapor. So in this early phase of the ocean's disappearance, it's the tropics that are working hardest, releasing more moisture into the air than usual, feeding more water vapor up into the atmosphere where the sun can get to it. And once that extra water vapor is up there, something interesting happens. Sunlight, specifically the ultraviolet end of the spectrum, is energetic enough to break water molecules apart through a process called photodissociation. It's exactly what it sounds like: light destroying a chemical bond. A photon hits a water molecule and the molecule splits. Hydrogen and oxygen separated. And then the hydrogen, being the lightest element in the entire universe, lighter than anything else, really by a significant margin, begins to drift. It rises through the atmosphere, thinning as it goes, until eventually it crosses the boundary where Earth's gravity no longer has a strong enough grip, and it escapes into space, into the vast and permanent dark between the stars. And it doesn't come back. The oxygen, on the other hand, isn't going anywhere quite so easily. Oxygen is heavier, and it also happens to be extraordinarily reactive. Left behind when the hydrogen departs, a lot of that extra oxygen would find something to bond with almost immediately. It would react with rocks, iron-rich rocks turning red and rusty as they oxidized. It would react with metals exposed at the surface. It would react with volcanic gases pouring out of vents and fissures. The chemistry of the Earth's surface would begin very gradually to shift. The extra oxygen wouldn't just pile up in the atmosphere. It would get absorbed, locked away in minerals, buried in the slow geological memory of the planet. Meanwhile, back at the surface, the oceans would be getting ever so slightly shallower. Not in any way you could measure by walking into the sea and noticing the water at your knees instead of your waist. We're talking changes that would accumulate over timescales longer than recorded human history. But shallower all the same. And shallow water behaves differently than deep water. It warms faster. Sunlight that would have been absorbed gradually through hundreds of meters of depth now reaches the seafloor in some places where it never used to. The thermal buffer that deep oceans provide, that enormous capacity to absorb heat and release it slowly, keeping things relatively stable, would begin to weaken. Marine heat waves, which are already becoming more common in our current world, would grow more frequent and more severe. Stretches of ocean that were once reliably temperate would swing into dangerous heat. Coral, fish, the whole intricate web of life that depends on stable ocean temperatures, all of it would come under increasing pressure. And the atmosphere above those warming waters would feel the change too. Before the oceans were gone, before they'd lost enough volume to truly shrink, there would be a strange and violent middle period where storms grew stronger. Hurricanes and typhoons and cyclones are powered by warm ocean water. They draw heat and moisture up from the surface and turn it into wind and rain. Warmer, more energetically evaporating seas would feed those storms with more fuel than they were used to. So in this early phase of disappearance, the planet might actually see bigger storms, not because of abundance, but because of a kind of last flourishing before the decline. The ocean gave more than it could afford to, spending itself on weather. There's something almost cinematic about that. These massive, swirling systems growing over a sea that is, in a geological sense, already beginning to go. As though the atmosphere is drawing one long, dramatic breath before the silence sets in. And silence is the right word to reach for, in a way. Because here is something easy to forget about the ocean. It's not just water. The sound. The ocean is one of the most persistent and widespread sources of ambient noise on the planet. Waves break on coastlines thousands of kilometers long. The deep, low rumble of swells crossing open water. The hiss of surf. The rhythm of tides. The constant conversation between water and shore. Even far inland, Even in the middle of a continent, the acoustic fingerprint of the ocean reaches you in subtle ways. In weather, in the moisture content of the air, in the behavior of the atmosphere itself. As the oceans began to shrink, that sound would change. Coastlines that once met the sea would slowly be left behind. The long, grinding music of waves on rock and sand would pull back, retreating with the waterline. And in its place, quieter air, stiller horizons, a planet learning, over an unimaginable span of time, what it sounds like without the ocean's voice. It would be gradual, of course. Everything about this is gradual. But that's almost the point. The first invisible changes are invisible precisely because change at this scale doesn't announce itself. It just begins, quietly, in the warmth of the tropical seas, in the drift of hydrogen atoms past the edge of the atmosphere, in the slightly stronger storms, in the very, very slowly falling tide. The oceans are still here, for now, for a long, long time still to come. But something has shifted, and somewhere, in a future so distant it exists more as a concept than a place, the world is already a little different than it was. There's a version of this world that most of us have never seen and never really think about. It exists right now, beneath the surface of the ocean. A vast, intricate landscape of plains and mountains and cliffs and canyons, spread across the majority of the planet's surface, hidden under kilometers of water. It has its own geography, its own geology, its own strange and ancient history, and almost none of it has ever been touched by sunlight. But it's there, all of it, waiting, as the oceans begin their long retreat. That hidden world would start, piece by piece, to the surface. This wouldn't happen quickly. Nothing about this process happens quickly. But over thousands of years, then tens of thousands, then hundreds of thousands, the waterline would drop. Slowly at first, barely perceptible even over generations, and then more noticeably as the rate of loss compounded across time. The sea would pull back from the land the way a tide goes out, except this tide would never fully come back in. And as it retreated, it would leave behind something extraordinary. The first thing that would happen almost immediately in geological terms is that the coastlines would begin to move. This might sound simple, but think about what that actually means. Every coast on Earth, every beach, every port city, every cliff face that has ever had waves breaking against it, exists where it does because that's where the land meets the sea right now, at this particular moment in the planet's long history. But sea levels have never been permanent. They have risen and fallen many times over Earth's billions of years, and every time they changed, the coastlines changed with them. During the last ice age, when enormous amounts of water were locked up in glaciers and ice sheets, sea levels were roughly 120 meters lower than they are today. Vast areas that are now shallow seafloor were dry land. The English Channel was a river valley. The islands of Southeast Asia were connected to the Asian mainland. Humans walked across land bridges that are now submerged beneath tens of meters of ocean water. What we're imagining now is something far more extreme than that and far more gradual, but the principle is the same. As the water level dropped, the coastlines would move outward. Not by meters, but eventually by kilometers. Then tens of kilometers. Then hundreds. The shallow coastal seas, the parts of the ocean that sit over what geologists call the continental shelf, would empty first because they're the shallowest, and as the water retreated it would expose something that no living thing had ever seen under open sky. Mud. Vast, dark, ancient mud. The seabed along coastlines and continental shelves is not rock. It's sediment. Centuries upon centuries of accumulated material, washed down from rivers, settled from the water column, built up layer by slow layer over millions of years. When it emerged into open air for the first time, it would be soft and dark and wet. It would smell extraordinary. That deep, mineral, biological smell of mud that has never been exposed to air. It would be utterly barren, at least at first. Nothing growing. No soil, no roots, just the raw material of what the seafloor used to be, blinking in an unfamiliar sun. And as far as you could see in every direction, it would stretch. These continental shelves are enormous. The shelf off the eastern coast of North America extends hundreds of kilometers out to sea. The shelves around Northern Europe, around Australia, around parts of Asia, they are wide, flat, gently sloping plains that currently lie under relatively shallow water, and as that water drained away, they would become the newest land on Earth. Flat plains of exposed seabed, stretching from the old coastlines out toward where the ocean used to be. No rivers would flow across them yet. No wind would have carved them into any familiar shape. They would just be there, immense and featureless and strange, the newest landscape on a very old planet. But the shelves are only the beginning, because beyond the shelves, the ocean floor drops away. And what lies beyond is something altogether more dramatic. At the edge of the continental shelf, in most parts of the world, the seafloor doesn't just slope downward, it falls. Dramatically, in some places, these are the continental slopes and rises, and further out, the abyssal plains, and they contain some of the most spectacular topography on the planet, none of which has ever been seen by human eyes in daylight. Underwater cliffs, real ones, not the kind you'd find on a coastline, worn smooth by waves and weather, but sheer, immense walls of rock, some of them taller than any skyscraper ever built. The Great Bahama Bank, off the Bahamas, has an underwater escarpment that drops thousands of meters nearly vertically. There are walls like this in the deep ocean all over the world, geological features formed by ancient faults and the slow drift of tectonic plates. And as the ocean level dropped, these walls would slowly emerge from the water 1 meter at a time until they stood in open air. Enormous, stark, dripping. Imagine standing at the base of one of those cliffs, or rather, where the base would be, since you'd be standing on what used to be deep ocean floor, and looking up at hundreds or thousands of meters of vertical rock face, dark with moisture, streaked with minerals, vast and completely silent. No birds, no moss, no sound except the wind, if there was any. Just rock. Ancient, newly exposed rock that had been underwater since before humans existed. And then, as the retreat continued, something even more surprising: mountains. We think of mountains as landlocked things, the Himalayas, the Andes, the Alps, but the ocean floor has mountain ranges too, and they are extraordinary. The mid-ocean ridge system, which runs through the Atlantic, Indian, and Pacific Oceans, is the longest mountain range on Earth. It stretches some 65,000 kilometers. It is continuous. It dwarfs anything on land, and most of it sits kilometers beneath the surface of the sea, completely unknown to the casual imagination. As the oceans fell, these mountains would rise. Not in the tectonic sense, they wouldn't actually be moving upward, but the water around them would be dropping, and the effect would be the same. The peaks would break the surface first, appearing as small islands in a shrinking sea. Then the upper slopes would emerge, and then more, and gradually the full scale of these submerged mountain ranges would be revealed. New chains of islands appeared across the ocean basins, at first barren and rocky, eventually spanning thousands of kilometers in long, sweeping arcs across what used to be open water. They would be completely unlike anything you'd expect from land that's newly appeared. No beaches, at least not yet. No river valleys or glacial carving. Those things take time and weather that hasn't happened here yet. Just the raw geology of the mid-ocean ridge, basaltic rock formed at the spreading centers where tectonic plates pull apart, dark and rough and entirely new to the sun. And some of those mountains would not be dormant. The ocean floor is one of the most volcanically active places on Earth, something that's easy to forget because it's hidden from view. The mid-ocean ridges are essentially continuous volcanic systems, where magma wells up from the mantle and creates new seafloor. There are thousands of submarine volcanoes scattered across the ocean basins, most of them unknown except to scientists. Some of them are actively erupting right now, quietly kilometers below the surface with nobody watching. As the water level fell around these volcanoes, they would emerge into the open air, and the interaction between hot magma and retreating seawater would be spectacular and violent in places. Steam, explosions, new lava flows meet the air for the first time, hardening into strange shapes as they cool. Volcanic islands rising from what used to be open ocean, building themselves upward even as the water around them dropped. The Pacific Ocean, which sits over several major volcanic hotspot chains, the same ones that built Hawaii, that built the Galapagos, would begin to reveal those chains in their entirety, vast lines of volcanic landforms stretching across thousands of kilometers of what had been open sea. Steaming, growing, entirely alien. And then there is the deep, the truly deep. The Mariana Trench in the western Pacific Ocean is the deepest known place on Earth. At its lowest point, the Challenger Deep, the seafloor sits nearly 11 kilometers below the surface of the ocean. More people have stood on the moon than have visited the bottom of the Mariana Trench. It is one of the most remote, most extreme, most inhospitable environments on the planet, and it exists in total, permanent darkness under crushing pressure. As the oceans retreated, the Mariana Trench would not disappear. It would transform. The water draining away around it would eventually expose the edges, then the upper walls, and finally, over an unimaginable span of time, the floor itself. What would be revealed is a canyon of staggering proportions. Nearly 11 kilometers deep. That is deeper than Mount Everest is tall. If you stood at the rim and looked down, the far wall would be invisible in the haze. It would be, by a very large margin, the deepest canyon on the surface of any world we know of. Vast, shadowed, geologically raw, and at the bottom of that canyon, and across the floors of the former ocean basins, and on the slopes of the newly emerged underwater mountains, and on the wide flat plains of the continental shelf, something else would be waiting. Light. Sunlight reaching the ocean floor is not something that normally happens. Even in the clearest, shallowest tropical waters, sunlight only penetrates a few hundred meters before it fades to blue dimness and then to total darkness. The deep ocean floor, the abyssal plain, the hadal zone at the very bottom of the trenches, has existed in complete and permanent darkness for hundreds of millions of years. Longer, in some places, than that. The sun has never touched it. Not once. As the water retreated, sunlight would fall on that floor for the first time. Slowly, first through kilometers of water that would filter it into a faint and distant glow, and then more directly as the depth decreased, and then, eventually, fully. Raw sunlight, the same light that warms your face in the morning, landing on rock and sediment that had never experienced it in all of geological time. What would it illuminate? Among other things, a record. The ocean floor is one of the great archives of Earth's history. Sediment settles on it continuously. Particles of rock, shells of microscopic organisms, dust from the continents, ash from ancient volcanic eruptions, and it accumulates in layers, year after year, millennium after millennium, building up a record of everything that has ever happened above it. It is undisturbed down there. No wind to erode it. No rain to wash it away. No footsteps to scatter it. Just the slow, silent accumulation of time. In that sediment you would find ripples, the preserved impressions of currents that flowed across the seafloor millions of years ago, hardened into place and then buried under subsequent layers, exposed now by the retreating sea. You would find tracks, the trails of ancient creatures that crawled and burrowed across the bottom, in some cases in eras so remote they predate the existence of any land animal. You would find chemical gradients and microscopic structures and the compressed remains of organisms that lived and died in the darkness long before anything walked on land. It would be, in a very real sense, a museum of deep time. Not a museum anyone built or anyone curated. Just the honest record of a planet doing what planets do. Accumulating history in the dark, layer by patient layer, waiting without knowing it was waiting for the day the light finally came. That day would be strange and quiet and enormous. The sea is pulling back. The land is emerging. The mountains rising from the water. The trenches open to the sky. The world is getting bigger, in a way, more surface, more topography, more land than any map had ever shown. Even as the thing that made it what it was slowly, gently disappeared. For a long time, the ocean would still look like the ocean. That's the thing that makes this part of the story so quietly devastating. The water would still be there, blue and vast and moving, still catching the light in the morning the way it always has, still pulling tides up beaches, still stretching to the horizon in every direction. Ships could still sail on it. You could still swim in it. From a distance, from the deck of a boat in the middle of the sea, you might not notice anything different at all. But beneath the surface, the world would already be coming apart. Life in the ocean did not arrange itself randomly. Every creature, every ecosystem, every food web that exists beneath the waves is the product of millions of years of adaptation to specific conditions, specific depths, specific temperatures, specific pressures, specific chemistry. The ocean is not one place. It is thousands of places stacked on top of each other and spread across the globe, each one precisely tuned, each one dependent on the others in ways that are sometimes obvious and sometimes so subtle we're still discovering them. And when you start changing the conditions, even slowly, even gradually, the tuning starts to go wrong. The first losses would come from the places closest to the surface, because those are the places most exposed to the changes already building in the atmosphere and the warming water. And among the very first to go would be the reefs. Coral reefs are often called the rainforests of the sea, and the comparison is fair. They cover less than 1% of the ocean floor but support somewhere around a quarter of all known marine species. They are dense, intricate, endlessly varied, and they are also extraordinarily sensitive. Coral polyps, the tiny animals that build the reef structure, live within very narrow tolerances. Temperature a degree or two above normal for long enough and the coral bleaches, expelling the photosynthetic algae that live inside it and give it color, essentially starving itself in slow motion. Change the chemistry of the water, change the light levels, change the depth, and the whole structure begins to falter. In our scenario, the reefs would be hit from multiple directions at once. The water warmed as it grew shallower, the sea level dropping so that reefs which once sat at a comfortable depth below the surface would find themselves closer and closer to open air, exposed to more intense sunlight, to wave energy they weren't designed to handle so directly, and eventually, in some places, to air itself. Coral exposed to open air dies quickly. Simply not built for that. The structure remains for a while, the calcium carbonate skeleton, bleached and brittle, but the living organism is gone. The reefs would go quiet. The fish that sheltered in them and fed among them would scatter, looking for habitat that no longer existed at the same scale. The colors, those extraordinary, improbable colors that make a healthy reef look almost artificial, like something imagined rather than grown, would fade. The structure would crumble over time as the physical forces that once kept it intact no longer balanced. And then the kelp would go. Kelp forests are one of the most productive ecosystems on the planet. They exist in cold, nutrient-rich coastal waters, the kelp itself growing from the seafloor, sometimes reaching heights of 50 meters or more, forming a kind of cathedral underwater, with a canopy at the surface and open space below. Sea otters sleep floating in it. Fish move through it in great schools. The whole ecosystem is built around the presence of the kelp, and the kelp is built around the presence of a specific kind of coastline, shallow, cold, close to shore. As the shorelines retreated, those kelp forests would be left behind. The water they needed would drain away. The seafloor they were anchored to would emerge into the open air. The kelp, deprived of the water it needs to photosynthesize and grow, would dry out. Collapsing slowly, the fronds drying and curling, the stipes breaking, the holdfasts losing their grip on a seafloor that was no longer a seafloor. Enormous stretches of what had been one of the most vibrant underwater landscapes on Earth would become dry, tangled wreckage on a mudflat. Everything that depended on those forests would have to move or adapt or disappear. The fish would feel the pressure from every direction. It wouldn't begin with a mass die-off. It would begin with crowding. As the oceans shrank, the total available habitat would shrink with them, and the populations of fish and other marine animals that had spread across those habitats would be compressed into smaller and smaller volumes of water. More competition for food. More competition for space. Predator and prey pushed together in ways that disrupted the normal dynamics that kept both populations stable. Overfishing, disease, the collapse of food sources. All of these would accelerate in a smaller, warmer, more crowded ocean. Species that had previously been stable would begin to decline, then decline faster, then, in some cases, simply be gone. The sheer diversity of ocean fish life, the extraordinary variety of species that fill every conceivable niche from the sunlit surface to the deep abyssal plain, would begin to thin. Not all at once, not evenly, but steadily and without reversal. Long before the oceans were gone, the fishing would have ended. The age of human seafood would be over, and the giants of the ocean would face their own particular crisis. Whales are the largest animals that have ever existed on this planet. The blue whale, the biggest of them all, can grow to 30 meters long and weigh 150 tons. And the reason an animal that size can exist at all is, in large part, because of the ocean. Water provides buoyancy. It supports the whale's body against gravity in a way that air simply cannot. A blue whale on land would be crushed under its own weight within hours. Its entire biology is premised on existing in deep water, where the pressure and buoyancy are consistent and the whale can move through 3 dimensions without the full force of gravity bearing down on it. As the oceans became shallower, that buoyancy would become harder to find. The deep, open water that whales need to dive, to feed, to navigate their vast migratory routes, it would be shrinking. Whales would be forced into shallower water, where the buoyancy was less reliable, where the pressure dynamics were wrong, where the krill and deep water prey they depended on were themselves disappearing. Some species would strand themselves, not by accident or disorientation as sometimes happens today, but because the ocean had simply become too shallow to hold them. The physics that made their existence possible would be failing. There is something particularly affecting about imagining the whales in this scenario. These animals that have navigated the deep ocean for tens of millions of years, that communicate across ocean basins in low, resonant frequencies, that have cultures and memories and relationships that persist across decades, being gently, inevitably pushed toward a world that can no longer contain them. Deeper still, the losses would be just as profound, just in a different key. The deep ocean has its own creatures, built for a world that most of us never think about and few people have ever seen. Anglerfish, with their bioluminescent lures dangling in total darkness. Giant squid, with eyes the size of dinner plates, evolved to detect the faintest traces of light. Creatures that have adapted over millions of years to the cold, the dark, and most importantly, the pressure, the immense, crushing weight of kilometers of water pressing down from above. Pressure at depth is not incidental to deep-sea life. For many of these animals, it is fundamental. Their biology, their cell membranes, their metabolic processes, the very proteins that make their bodies work, is calibrated to function under conditions that would kill a surface animal instantly. As the water above them decreased, the pressure would decrease with it. And without that pressure, without that specific ancient environment, these creatures would simply stop being viable. Their world would be shrinking from above, the water retreating, the weight they depended on lifting, and there would be nowhere for them to go. The hydrothermal vent communities would face a different end, but an end all the same. Hydrothermal vents are among the most remarkable places on Earth. They exist at the bottom of the ocean, usually along tectonic boundaries, where superheated water rich in minerals vents up from the seafloor. They are completely cut off from sunlight. The ecosystems there are not based on photosynthesis at all, but on chemosynthesis, where bacteria convert the chemical energy of the vent fluids into biological energy. And built on top of that foundation, extraordinary communities of life. Tube worms meters long, ghostly pale crabs, strange eyeless shrimp, fish and mollusks adapted to heat and chemistry that would be lethal anywhere else. These ecosystems are isolated, ancient, and entirely dependent on the specific physical conditions of the deep ocean, the pressure, the cold surrounding water, the chemistry of the vent fluids mixing with seawater. As the ocean above them retreated, as the depth decreased and the pressure changed, as the surrounding water warmed and its chemistry shifted, the conditions that made vent life possible would deteriorate. These communities, which may have survived largely unchanged through geological upheavals that reshaped the rest of the planet, would finally find an ending. And then there is the foundation of everything. Plankton, specifically phytoplankton, the microscopic photosynthetic organisms that float in the sunlit upper layers of the ocean in numbers so vast they are essentially uncountable. They are the base of the marine food chain. Everything in the ocean, from the smallest fish to the largest whale, depends in some way on the energy captured by phytoplankton. They are also, in a very direct sense, the reason you can breathe. Phytoplankton produce somewhere between 50 and 80% of the oxygen in Earth's atmosphere. Let that sit for a moment. The oxygen in roughly every other breath you take was produced not by a forest or a meadow but by microscopic organisms floating in the surface of the ocean, organisms so small that millions of them fit in a single drop of water. They are, without much exaggeration, the lungs of the planet. As the oceans warmed and changed and shrank, different species of phytoplankton would struggle. Some would vanish entirely as their preferred conditions disappeared. The whole community would shift, the species composition changing, the overall abundance declining in many areas. And as the phytoplankton declined, two things would happen in parallel. The food chains built above them would begin to collapse from the bottom up, and the oxygen output of the ocean would fall. Not quickly enough to be felt in a single lifetime. Not fast enough to make headlines in the way a catastrophe does. But measurably, steadily, the air itself, over the course of the long centuries, became a little thinner, a little less rich, as the engines that had maintained it for billions of years slowly wound down. The animals that needed the coast would lose their footing too. Sea turtles have been navigating the oceans and returning to the same beaches to nest for over 100 million years. They predate the extinction of the non-avian dinosaurs. They find their nesting beaches through some combination of magnetic field navigation and memory that we still don't fully understand, returning, sometimes across thousands of kilometers of open ocean, to the exact stretch of sand where they were born. And as the coastlines moved, as the beaches they'd navigated to for generations retreated or disappeared entirely under new mud and exposed shelf, that ancient GPS would point to places that no longer existed. Seals, sea lions, walruses, all the animals that depend on specific coastal habitats for breeding, for resting, for raising young, would face the same problem. The coast was always there. It was the fixed point around which their whole life cycle was organized. And now it was moving faster than evolution could follow. But not every species would simply disappear. Life is stubborn, and the ocean, even a shrinking one, would still be full of places to hide and ways to adapt, at least for a while. As the great ocean basins fragmented, as shallow sills between ocean regions emerged above water level, as island chains rose to divide open sea into enclosed basins, as the retreating water left behind chains of lakes and inland seas and isolated gulfs, some marine species would find themselves cut off. Populations that had once moved freely across the open ocean would now be separated by new land, confined to pockets of water that were growing smaller and more different from one another with every passing generation. And in those pockets, something interesting would happen. Evolution, given enough time and enough isolation, always does something interesting. Species separated from their relatives would begin to diverge. Different selective pressures in different isolated environments would push them in different directions. Coloration, behavior, body shape, tolerance for heat or salinity. All of it drifting as each population adapted to its own shrinking world. Thousands of years would pass. The separated populations would become something new. Not quite the same as what they'd been before. New species, perhaps, or the beginnings of them, emerging from the wreckage of the old ocean ecosystem, finding small footholds in a world that was no longer built for them but hadn't finished with them yet. Life finding a way, as it always has, as it always does, even here, even now, even as the ocean slowly, inevitably pulled back from the world it had made. There is a map that most people have never seen, and it has nothing to do with land or borders or the names of countries. It is a map of movement, of the great rivers that flow through the ocean itself, invisible beneath the surface, carrying enormous volumes of water and heat around the planet in slow, continuous loops. These are the ocean currents, and they are, in a very real sense, the reason the world's weather works the way it does. The most famous of them is the Gulf Stream. It begins in the warm waters of the Gulf of Mexico, sweeps north along the eastern coast of North America, and then curves across the Atlantic toward Europe, carrying with it water that is significantly warmer than the surrounding sea. That warmth bleeds into the atmosphere above it, and the atmosphere carries it east, and the result is that Western Europe, which sits at roughly the same latitude as Canada, has a climate that is dramatically milder than it has any geographic right to be. London is at the same latitude as parts of Newfoundland. Amsterdam lines up with Calgary, Oslo with southern Alaska. Without the Gulf Stream, the winters across much of northern and western Europe would be a different thing entirely. And the Gulf Stream is only one thread in a much larger tapestry. The whole system, sometimes called the global ocean conveyor belt, or the thermohaline circulation, connects the Atlantic to the Pacific to the Indian Ocean to the Southern Ocean in one continuous, slow-moving loop. It moves heat from the tropics toward the poles. It carries cold, nutrient-rich water up from the deep in certain places, feeding the surface ecosystems that depend on it. It keeps the climate of the entire planet more stable and more moderate than it would otherwise be. And it runs on water, specifically on differences in the temperature and salinity of water in different parts of the ocean, differences that drive the density gradients that keep the whole circulation moving. Change the water, change the circulation. And as the oceans began their long retreat, the circulation would begin, gradually and then with increasing certainty, to fail. It wouldn't stop all at once. These are not systems with clean-off switches. But as the volume of water decreased, as the surface area shrank, as the temperature gradients that drove the currents were disrupted by a warming and changing ocean, the flow would weaken. The Gulf Stream would slow. The conveyor belt would lose its rhythm. And the effects of that would ripple outward across the climate in ways that were deeply counterintuitive, because what the circulation does, moving heat around, means that its absence would make some places colder and some places hotter in patterns that didn't follow any simple logic. Western Europe would feel it first and most dramatically. The mild winters that the Gulf Stream had been providing for thousands of years would become something harder. Not overnight, not even within a generation. But over centuries, the shift would be undeniable, average temperatures dropping in places that had come to depend on the warmth of the current, winters lengthening, the agricultural and ecological patterns that had developed under milder conditions coming under strain. Some cities that had been temperate would begin to feel something closer to subarctic. Some forests would struggle. Some farming regions would find their growing seasons shortened in ways that had no precedent in recorded history. And meanwhile, on the other side of the same equation, the cold currents. The ocean doesn't just redistribute warmth. In some places, it actively cools the land nearby. The California current, flowing south along the western coast of North America, keeps coastal California and the Pacific Northwest cooler and foggier than they would otherwise be. The Humboldt Current, flowing along the western coast of South America, does the same for Peru and Chile, keeping those coastal regions surprisingly temperate despite their low latitude. The Benguela Current keeps the coast of southern Africa from getting as hot as the interior. These cool currents work in the opposite way from the warm ones. They bring cold water up from the deep and push it along coastlines, chilling the air above them. As the ocean shrank and the currents weakened, this cooling effect would diminish. Coastal regions that had been kept relatively cool would warm. The fog banks would disappear. The temperature moderation that the current had provided would be gone. Some coastal areas would become significantly hotter than any living thing that had evolved there was prepared for. Hot where it used to be cool, cold where it used to be warm. The familiar map of the world's climates, which had been relatively stable across the whole of human civilization, scrambling into something unfamiliar. But the deeper change, the one that would ultimately reshape more of the planet's surface than any shift in temperature, would be something simpler and more fundamental. The clouds would go, or rather, they would become less common. Fewer of them in more and more places, covering less and less of the sky. The ocean is where weather comes from. Not all weather, but most of it, and the most important of it. The ocean is Earth's largest source of atmospheric moisture, the vast evaporating surface that loads the air with water vapor, which then rises and cools and condenses into cloud, and eventually falls back down as rain or snow. The whole system, what we call the water cycle, the hydrological cycle, is fundamentally powered by the ocean's surface and the energy of the sun acting on it. As the ocean shrank, that source would diminish. Less surface area evaporating means less moisture entering the atmosphere. Less moisture in the atmosphere means fewer clouds forming. And fewer clouds means less rain. This is not a small thing. This is not a regional inconvenience. This is a fundamental change in how the planet moves water around, and the consequences of it would propagate through every ecosystem, every river system, every aquifer, every forest on Earth. The water cycle would slow down. The great, ancient rhythm of evaporation and precipitation that had kept the continents wet and habitable for hundreds of millions of years would lose its engine. Not stop entirely. There would still be some ocean, for a very long time, still evaporating, still feeding clouds, still producing rain. But less. Always less. And the effects would compound over time. Rainfall patterns across the world would shift in ways that were difficult to predict and impossible to adapt to quickly. Some regions that currently receive regular, reliable rainfall would find themselves in increasingly long dry spells. Seasons that used to bring monsoon rains would arrive with diminishing returns, the rains lighter and shorter and less certain each time. Forests that had been sustained by consistent precipitation would begin to dry at their edges, the canopy thinning, the undergrowth turning brown, the whole system gradually giving way to something drier and more open. Some places would become dry plains where forests had stood. Others would become outright deserts. Not necessarily the hot, sandy kind, but the cold, rocky, empty kind, swept by dry winds that carried dust instead of rain. The line between habitable and uninhabitable land would shift, and not in humanity's favor. And the rivers would notice. Rivers are not self-sustaining. They depend on continuous inputs, rainfall onto catchment areas, snowmelt from mountains, the slow seepage of water from saturated soils into stream channels. Take away the rain, reduce the snowfall, dry out the soils, and the rivers have nothing to carry. They shrink. They become seasonal. They stop flowing in summer. And then, eventually, they stop flowing at all. Many of the world's great rivers would begin to fail long before the oceans were gone. The rivers fed by glaciers would go first as the glaciers shrank, and the glaciers would be shrinking fast in a world with less snowfall and more warmth. The rivers fed purely by rainfall would follow. The Amazon, sustained by the extraordinary moisture recycling of the rainforest itself, would hold on longer than most, but as the surrounding forest dried and the atmospheric moisture declined, even that would eventually thin to something unrecognizable. There is something genuinely strange to sit with about a river running dry. Rivers have been among the most permanent features of the human world. The things civilizations built themselves around, the things that seemed as fixed and eternal as the mountains they ran between. The Nile, the Ganges, the Mississippi, the Yangtze, these are not just rivers, they are the organizing principles of entire cultures, entire histories. And they would simply stop. Dry beds of gravel and sand and bleached rock, tracing the paths where water used to run. The storms would change too, and this time the change would be a quieting rather than an intensification. Hurricanes, typhoons, cyclones, all the great tropical rotating storms that are among the most powerful weather events on Earth are powered by warm ocean water. They form when warm, moist air rises rapidly from a heated ocean surface, drawing in more air behind it, setting up the rotation, feeding on the energy difference between the warm water below and the cold air high above. Take away the warm ocean surface, take away the depth and extent of warm water that fuels these systems, and the storms weaken. This is the reversal of what happened in the early stages. In Act 1, when the oceans were still full but warming, storms grew stronger. Now, as the oceans shrank and the vast warm expanses of tropical sea grew smaller, the fuel for those storms would diminish. Hurricane season would become less intense. The great storms that had shaped coastlines and terrified sailors and driven whole populations inland would come less frequently. Some years, perhaps none at all in regions that had once expected them reliably every season, which might sound like a relief, and in the short term, in the local sense, it would be. But the energy that those storms had been moving, the heat they transferred from the tropics toward higher latitudes, the rain they dropped across land that depended on it, none of that would simply disappear. It would just stop being redistributed. And the consequences of that, folded into everything else that was already changing, would be difficult to untangle from the larger unraveling. The snow would go quiet too. Mountain glaciers are, in a way, the banks of the world's water system. They accumulate snow in winter, store it in ice, and release it slowly through the warmer months as meltwater, feeding the rivers and aquifers that billions of people depend on. They buffer the water supply, providing water precisely when rainfall is least reliable, when the rivers would otherwise run low. But glaciers depend on snowfall to maintain themselves. Enough snow has to fall each winter to replenish what melts each summer, or the glacier shrinks. In a world with less atmospheric moisture, with a weakened water cycle producing less precipitation overall, snowfall in mountain regions would decrease. The glaciers would melt faster than they accumulated. One by one, over generations, the great ice masses of the Himalayas and the Andes and the Alps and the Rockies would diminish and eventually vanish, leaving behind bare rock and the dried-out river valleys that had depended on them. And then there is something smaller, something quieter than all of this, something so commonplace that its rarity would itself become a kind of loss. Rain. Not the absence of oceans, not the failure of rivers, not the retreat of glaciers, just rain. The ordinary, everyday rain that falls on an ordinary afternoon. The sound of it on a roof. The smell of it on dry ground. The gray light it brings and the coolness behind it, and the way everything looks washed and new when it stops. Rain is so unremarkable in a world with full oceans that we complain about it. We build our umbrellas and our drainage systems and our overhangs around managing it, redirecting it, getting out of its way. In this future world, rain would become something else. It would come rarely enough in many places that its arrival would be an event. People would notice it. They would step outside to feel it. Children who had grown up in the dry years would encounter a proper rainstorm and not quite know what to make of it. The libraries and archives of the world would have recordings of what heavy rain sounded like, and people would listen to them the way we listen to sounds of nature that have faded from our immediate experience. Something so fundamental to life on Earth. Something that had been present in every age, in every era, in every human story ever told. Becoming rare, becoming precious, becoming, in some regions, a memory. The planet is getting quieter and drier. The sky is growing clearer in the way that cloudless skies always look clear, vast and blue and empty and, finally, just a little bit too still. There is a word that geologists use for the process by which a landscape loses its water and becomes something drier and harder and more exposed. They call it desiccation. It's a clinical word, a precise word, the kind of word that appears in academic papers and field reports without any emotional weight attached to it. But the thing it describes, the slow, irreversible drying of a place that was once wet, is one of the most profound transformations a landscape can undergo. And in this stage of our story, it would be happening everywhere, all at once, across the entire surface of the planet. The world would be drying out, not uniformly, not all in the same way or at the same pace, but the direction of travel would be unmistakable. The moisture that had kept the continents green and habitable, that had fed the forests and the grasslands and the rivers and the soils, would be retreating back toward what remained of the ocean, and the land left behind would be changing in response, becoming harder, becoming paler, becoming a stranger. The deserts would lead the way. Deserts already exist at the edges of the climate system, in the places where the circulation of the atmosphere delivers dry air rather than moist air, where the ocean's influence is weakest, where rainfall has always been sparse. The Sahara, the Arabian Desert, the Gobi, the great deserts of Australia and southern Africa and the American Southwest. These are not empty places. They are full of their own life, their own beauty, their own ancient and adapted ecosystems. But they exist at the margins, held in place by the larger patterns of atmospheric circulation. As the ocean shrank and the water cycle weakened, those margins would expand. The dry zones would push outward into the semi-arid lands at their edges, into the grasslands that bordered them, into the savannas and the scrublands and the thin forests that had managed to survive at the limits of reliable rainfall. The Sahara would grow. The Australian interior would dry further. The grasslands of Central Asia, the Cerrado of South America, the vast semi-arid belts of multiple continents, all of them would feel the desert advancing at their backs. It wouldn't always look like what we picture when we think of the desert. Not all of it would be sand dunes and scorching sun. Some of it would be rocky and cold. Some of it would be flat and featureless. Some of it would be covered in the cracked, pale remnants of soil that had once been productive. A landscape that looked like it was waiting for rain that was never going to come. And then there would be the salt. In the shallowest places, the regions where the ocean had been thinnest, where the continental shelf had risen first into the open air, the retreating seawater would leave something behind. Water evaporates. Salt doesn't. Every shallow sea that dried up, every coastal bay that was cut off and emptied, every inland extension of the ocean that lost its connection to the main body of water and slowly evaporated under the sun, would leave behind a residue of salt. A thin crust at first, then thicker, then vast, blinding white expanses of crystallized minerals stretching in every direction. We have places like this on Earth today. The Bonneville Salt Flats in Utah, the Sala de Uyuni in Bolivia, the salt pans of the Makgadikgadi in Botswana. These are places where ancient lakes and seas dried up and left their mineral content behind, and they are among the most otherworldly landscapes on the planet. Flat to the horizon, white as fresh snow, utterly barren, shimmering in the heat. They are beautiful in a desolate way, the kind of beautiful that makes you feel the absence of something rather than the presence of it. In the world we're imagining, Landscapes like this would form across enormous areas. The floors of former shallow seas, stretching for thousands of kilometers. Not just small salt pans, but continental-scale salt flats, white and hard and endless, where the bottom of an ocean used to be. The light reflected off them would be extraordinary, visible from space, perhaps, as great white expanses marking where the sea had been. During the day, the glare would be almost unbearable. At night, the temperature would plummet onto a surface that absorbed no warmth and held nothing back. The salt would not stay put. One of the things that salt flats do, when they dry out completely and the crust begins to fracture, is produce dust. The wind picks up the surface material, tiny crystals of salt and mineral, fine as powder in places, and carries it. And in a world where the former ocean basins were wide and flat and exposed, and the winds would be blowing across them with nothing to slow them down, the dust storms that resulted would be unlike anything in our current experience. We have seen some of what this can look like. The Aral Sea, once the fourth largest lake in the world, drained by Soviet irrigation projects over the second half of the 20th century, has left behind a salt flat in Central Asia that generates dust storms regularly now, carrying salt and toxic residue from the old seabed hundreds of kilometers downwind. The people who live near it breathe it. It lands on their crops, coats their windows and their skin. Scale that up by orders of magnitude. A former ocean basin, thousands of kilometers across, baking in the sun, its surface fracturing and powdering, the wind building across the flat expanse with nothing to obstruct it. The dust storms that rose from those basins would be visible on satellite imagery, if there were satellites left to see them. They would travel across continents. They would deposit salt on soils that were already struggling, further reducing their ability to support plant life. They would cloud the air and reduce visibility and carry the chemical signature of the ancient seafloor deep into the interior of continents that had never tasted salt before. The sand dunes would come next. It takes time for dunes to form, time for sediment to be broken down fine enough to move with the wind, time for the wind to sort and deposit it, time for the characteristic shapes to build. But the former ocean basins would eventually provide all the raw material needed. The deep sea sediments, those ancient layers of accumulated biological and geological material that had been building up on the ocean floor for hundreds of millions of years, would dry out as the water retreated. They would crack first great polygonal patterns in the surface, like the mud flats you see at the edges of dried-up lakes, but on a scale almost impossible to comprehend. Thousands of kilometers of cracked, ancient sediment, drying under a sun that had never reached it before. And as the wind worked on it, as the surface material broke down further and became fine enough to carry, the dunes would begin to form. Not the modest dunes of existing deserts, constrained by the size of the sand source and the geography around them. These would be dunes with an almost unlimited source of material, forming across the floors of former ocean basins that stretched further than any desert on Earth today. Dune fields larger than continents. Sand seas that would make the current Sahara look like a sandpit. In the middle of what had been the deepest ocean, in the places where the sediment had been building for the longest time, the landscape might eventually look something like the great ergs of the Sahara, wave after wave of sand, shaped by wind into forms of austere beauty, going on and on without any visible end. But the scale would be different. Everything about it would be different. There are places where a smaller version of all of this has already happened, and they tell us something important. The Mediterranean Sea in the distant geological past dried up. About 5 to 6 million years ago, during a period geologists call the Messinian salinity crisis, the connection between the Atlantic and the Mediterranean closed due to tectonic movement, and the Mediterranean, already a relatively enclosed body of water with high evaporation, began to dry. Over tens of thousands of years, it became a series of hypersaline lakes and then, in the deepest basins, effectively empty. a vast desert of salt and sediment sitting kilometers below the surrounding landscape, baking in a sun that had never reached it before. Eventually, the Atlantic broke back through what is now the Strait of Gibraltar, and the Mediterranean refilled in what must have been a geologically spectacular event. But the evidence of the drying remains, buried in the sediments beneath the current seafloor, enormous salt deposits laid down during that arid interlude, a reminder that even the Mediterranean is not as permanent as it seems. In our scenario, that refilling never comes. The Mediterranean, as the global ocean level dropped and the connection to the Atlantic narrowed and eventually closed, would become isolated. And then it would begin, once again, to do what it did 5 million years ago. Evaporate, concentrate, turn salty beyond the tolerance of life, and finally, slowly, become a salt basin. A deep, white, empty space where a sea had been, surrounded by the landscapes of southern Europe and North Africa, sitting like a wound in the geography of a former continent. The Black Sea would follow. The Caspian, already technically a lake, would shrink further. Enclosed seas and marginal basins around the world would reach their tipping points before the main ocean bodies did, each one going through its own version of the same transformation. Each one leaving behind its own ghost landscape of salt and sediment and cracked ancient mud. And across all of these landscapes, old and new, something fundamental about the climate would be shifting. Water is extraordinary at storing heat. This is one of its most important properties. The reason that coastal climates are milder than inland ones. The reason that places near the ocean don't experience the same violent swings between day and night temperature that desert regions do. The ocean absorbs heat during the day and releases it slowly at night. It absorbs heat in summer and releases it in winter. It is the great thermal buffer of the planet, smoothing out the extremes, keeping the range of temperatures that any given place experiences within reasonable bounds. Remove the ocean and the buffer is gone. The exposed ocean floor, now dry land and lots of it, would behave the way deserts behave. Without the moderating influence of water, without anything to absorb the sun's heat during the day and release it gradually at night, the temperature swings would become violent. The day surface could become scorching, far hotter than the current land surface at equivalent latitudes, and the night surface could plunge to bitter cold within hours of sunset. The range between daily high and low temperatures in the former ocean basins could be extreme in ways that current Earth doesn't experience except in the most continental and arid environments. And this effect would not be confined to the new dry land. It would bleed outward. Coastal regions that had always been buffered by their proximity to the ocean, that had enjoyed mild summers and winters that stayed above freezing, the classic maritime climate that makes certain parts of the world so livable, would find that buffer shrinking. As the sea retreated, as the moderating influence moved further away, the climate would become more continental. Hotter in summer, colder in winter, the range expanded in both directions. The seasons themselves would become more extreme. The difference between summer and winter, already a significant driver of how ecosystems and agriculture and human life are organized, would amplify. The summer would not just be warmer, it would be hotter than anything the region had previously known. The winter would not just be cooler, it would be sharper, more prolonged, more difficult. There is a word for this kind of climate. One that experiences large swings between seasons and between day and night, without the ocean to moderate it. Continental. It is the climate of the interior of continents, far from any coast, where the thermal mass of the ocean has no reach. In the world we're imagining, that continental climate would spread to cover most of the planet's surface. The mild, maritime climates that currently exist along coastlines and on islands would retreat as the coastlines moved outward and the islands were swallowed by new land. Eventually, almost everywhere would feel like the interior of a continent, because almost everywhere would be the interior of a continent. The Earth would become a harsher place, not in one dramatic moment, Not in any way that felt in a single lifetime like a rupture, just gradually harder, gradually drier, gradually more extreme. The slow accumulation of change, each individual shift small enough to absorb, the sum of them adding up to a world that resembled the old one in shape but not in feel. White salt flats where the shallow seas had been. Cracked ancient mud drying in the sun for the first time in hundreds of millions of years. Dunes building across the floors of ocean basins larger than continents. Storms of salt rising into air that was already too dry. Temperatures swinging wider each decade, each century, each millennium. The world is getting bigger and emptier and quieter. The ocean retreated further, always further. There is a version of history that no one has ever read. It exists, and it has always existed, but it sits beyond reach, buried under kilometers of water, preserved in sediment and salt and cold and dark, waiting with the particular patience of things that have no awareness of being waited for. It is a record of the planet stretching back further than any archive, any library, any fossil bed that human beings have ever had access to. It contains shipwrecks and cities and creatures and geological events and chemical signatures of ancient atmospheres. An almost incomprehensible layering of time, one era pressed down upon another, all of it resting quietly on the floor of the sea. As the oceans retreated, that record would surface. And the world, whatever the world had become by then, whoever was left to look, would find itself standing at the edge of the greatest archaeological and geological discovery in the history of the planet. Not a dig site, not an excavation, a revelation on a planetary scale. Thousands of kilometers of hidden history, slowly emerging from the water, blinking in a light it had never known. It would begin, as so many things in this story begin, gradually. The shallower regions first, the continental shelves, the shallow coastal seas, the marginal basins. And there, in the sediment, among the cracked mud and the drying salt crust and the strange new landscape of the former seabed, things would appear. The caves would be among the first surprises. Beneath the ocean floor, hidden not just by water but by the rock itself, there are tunnel systems and caverns carved by ancient water movement. Some of them formed by the same geological forces that build cave systems on land, others carved specifically by the movement of seawater through porous rock over millions of years. Underwater cave systems of extraordinary size exist in places like the Yucatan Peninsula, where the flooded cave network called the Sistema Sac-Acton stretches for hundreds of kilometers, much of it still unmapped. Similar systems exist beneath the seafloor in many parts of the world, inaccessible not just because of depth but because of the sheer volume of water filling them. As the water level dropped and those systems drained, they would open. Vast, silent spaces inside the rock. Chambers with ceilings that had never been exposed to air. Their walls still bearing the mineral formations that water deposits over centuries, stalactites and flowstone, and the delicate crystalline structures that only form in the dark over very long periods of time. Explorers entering these spaces would be moving through environments that had been sealed since before recorded history, breathing air that had never circulated, touching walls that had never been touched. And in the deepest, most inaccessible chambers, they might find things. The remains of sea creatures that had found their way into the cave system and died there, preserved by the cold and the chemistry of the water. Sediment layers that told the story of the ocean's history with extraordinary precision. In some cases, in the caves that opened up along coastlines that had been inhabited in prehistoric times, they might find something else entirely, evidence of human presence, from periods when sea levels were lower and the caves were accessible from land, before the rising seas of the post-Ice Age world sealed them beneath the waves. Which brings us to the ships. The ocean floor is, by a significant margin, the world's largest graveyard of human maritime history. Thousands of shipwrecks lie on the seabed, some in shallow water, accessible to divers and already partially explored, but many in the deep ocean, resting in conditions so cold and pressurized and oxygen poor that the preservation can be extraordinary. Wood that would have rotted away on land within decades has survived for centuries in the deep. Cargo remains in the holds. Objects that would have crumbled to dust in any terrestrial environment are still intact, still recognizable, still carrying the fingerprints of the people who made them and used them. As the ocean receded, these wrecks would emerge. The deep ones first appear as shadows in the retreating water, then gradually become visible, then accessible, then exposed to the air. Ships from every era of human seafaring, ancient Greek trading vessels, Roman galleys, medieval cogs, the great sailing ships of the age of exploration, the steel-hulled freighters and warships of more recent centuries. All of them scattered across the former seabed in the positions they came to rest in, sometimes sitting upright, sometimes on their sides, sometimes broken apart by the impact or by the long years since. The cargoes would still be there in many cases, amphorae packed with olive oil or wine from 2,000 years ago, the personal belongings of sailors who never made it home, documents sealed in waterproof containers that had kept water out for centuries, the logbooks of ships that disappeared without a trace, their last recorded positions the only clue to what happened and where they ended up. Imagine the libraries built from what was found, the museums, the rewriting of history, the trade routes confirmed or revised, the voyages reconstructed, the lost ships found and their stories finally told. But the ships would not be the oldest things recovered from the seabed. Beneath the wrecks, beneath the accumulated sediment of the historical era, beneath the layers of the last few thousand years of human activity, there would be something far older. Because the sea has not always been where it is now, and in the places where the sea came later, where land was drowned by rising waters after the last ice age 10 or 15,000 years ago, there would be the remains of the people who lived there before the flooding. We already know some of these places exist. Archaeologists have found submerged stone structures off the coasts of India, off Japan, in the North Sea, in the Mediterranean, the remnants of settlements that were coastal communities when sea levels were lower, now sitting under tens of meters of water. The Black Sea may have been a freshwater lake connected to the Mediterranean by a catastrophic flood around 7,000 years ago, an event that some researchers have connected to flood myths from multiple ancient cultures. These submerged landscapes are extraordinarily difficult to study underwater, and much of what lies there remains unknown. As the ocean retreated, those landscapes would resurface. The drowned coastlines of the post-Ice Age world, the places where people lived and built and fished and died before the sea took them, would reemerge. Not in their original condition, certainly. Thousands of years underwater leaves marks. But the foundations would be there. The tool deposits, the shell middens, the accumulated refuse of ancient coastal communities, which archaeologists prize precisely because they preserve organic material so well. The hearths, the burial sites, the docks and the fish traps and the stone walls of buildings that the sea swallowed before history had words to describe them. It would be the largest archaeological discovery ever made, spread across thousands of kilometers of newly exposed coastline, all of it available at once. And the people examining it, whoever they were in that far future, would be looking at the remnants of a world that predated their own by an almost incomprehensible span of time. The fossils would go even further back. The deep seafloor is one of the best fossil preservation environments on the planet. The cold, the pressure, the absence of oxygen in many regions, the slow and steady accumulation of sediment, all of these conditions work together to preserve organic material in extraordinary detail. Creatures that died in the deep ocean millions of years ago have left impressions and remains in the sediment that are, in some cases, more detailed and more complete than anything found in terrestrial fossil beds. As the sediment dried and hardened, slowly as the water retreated, those fossils would become accessible. Not just the familiar prehistoric marine creatures that we already know from existing fossil records, but organisms from the deepest layers of the ocean's history. Creatures from the Cambrian explosion, 500 million years ago, when animal life first diversified into the enormous variety of forms that would eventually lead to everything alive today. Organisms from the Precambrian, older still. The preserved remains of ancient ecosystems laid down in sediment at the bottom of seas that no longer exist in the form they once had, finally emerging into a world that had been waiting, without knowing it, to see them. And among those fossils, something stranger still, the preserved bodies of creatures from the deep ocean itself. In the oxygen-depleted zones of the former deep ocean, where decomposition had been slowed or stopped entirely by the absence of oxygen and the pressure of the water above, some organisms might be found in a state of preservation bordering on the remarkable. Not living, of course, not frozen in some science fiction sense, but intact, recognizable. The bodies of deep-sea creatures that had simply settled to the floor and been incorporated into the sediment before anything could break them down. Their soft tissues replaced molecule by molecule with minerals, their forms preserved in extraordinary detail. Future scientists examining these specimens would be looking at creatures that no living person had ever seen in anything other than the few blurry photographs taken by deep-sea cameras. Animals from a world so remote and so extreme that studying them had always required machines and submersibles and enormous effort. Now they would simply be there, in the dried sediment, waiting to be picked up and examined. The geology would be just as astonishing as the biology. The ocean floor is, in geological terms, a record of the planet's tectonic history. The scars left by earthquakes and submarine landslides are preserved on the seafloor with a clarity that the land surface rarely achieves, because the deep ocean is so free of the erosive forces that wear terrestrial landscapes smooth. On land, an ancient landslide is eventually blurred by rain and rivers and vegetation. On the ocean floor, it sits essentially unchanged for millions of years, the exact shape of the event frozen in place, the deposit laid down exactly as it fell. As the ocean floor was exposed, those frozen moments would become visible. The scars of ancient earthquakes, linear features cutting across the seafloor, offset rock formations marking where the ground had moved violently along a fault line. The deposits of submarine landslides, enormous fans of displaced sediment spreading downslope from the point where part of the continental shelf had given way, sometimes covering areas the size of small countries. Tsunami deposits, laid down by waves that had moved across the deep ocean floor when some ancient seismic event had disturbed the water above. These would be the geological equivalent of a crime scene preserved in amber, events that had happened millions of years ago, visible now in every detail, the sequence of what had occurred readable in the layers of sediment as clearly as words on a page. And deeper still, in the geology of the ocean floor itself rather than the sediment on top of it, the story of the planet's tectonic history. The mid-ocean ridges, those enormous underwater mountain ranges where new seafloor is created as tectonic plates pull apart, would be exposed in their entirety. And along them, and across the ocean basins they had built over hundreds of millions of years, the evidence of that building would be written in the rock. Transform faults, the boundaries where plates slide sideways past each other, offset sections of the ridge creating distinctive zigzag patterns across the seafloor. Fracture zones, the ancient traces of those same boundaries, preserved in the rock long after the active faulting had moved elsewhere. The magnetic striping in the basalt of the ocean floor, alternating bands of rock with different magnetic orientations, laid down as the Earth's magnetic field reversed over millions of years, recording the history of the planet's magnetism in the rock itself like the tracks of a tape recorder. Geologists looking at this exposed record would be seeing, for the first time, the complete and unobstructed history of how the ocean floor had been built. Not through seismic surveys and drill cores and the painstaking reconstruction of underwater data, but directly, with their eyes, walking across it, and they would smell it before they reached it. This is one of the details that is easy to overlook in thinking about a world of large-scale geological transformation. but it would be inescapable and overwhelming. The deep ocean sediment is full of organic material, the accumulated remains of billions of years of biological activity, compressed and buried and preserved in conditions that had prevented normal decomposition. When that material was exposed to air and warmth for the first time, decomposition would begin. And decomposition produces gases, sulfur compounds, methane, the chemical products of organic matter breaking down, releasing into the air everything that had been locked away in the sediment for millions of years. The smell of the newly exposed seafloor would be extraordinary. Not simply unpleasant, though it would certainly be that in places, but deep and strange and ancient, carrying chemical signatures that had not existed in the open air for longer than any human civilization had stood. It would be the smell of deep time itself, the planet's buried past releasing itself into the present, the accumulated biology of hundreds of millions of years of ocean life finally breathing out. In time, that smell would fade as the organic material finished decomposing and the sediment dried into something more inert. The ancient chemistry would stabilize. The exposed seafloor would become simply land, bare, mineral, strange, but no longer quite so powerfully reminiscent of what it had been. And people would come, because wherever there is newly exposed land, and wherever the conditions allow it, people eventually come. And what they would find on the former seafloor would be, among other things, extraordinary wealth. The ocean floor is extraordinarily rich in minerals and metals. Manganese nodules, potato-shaped lumps of mineral that form slowly on the seafloor over millions of years, litter the abyssal plains in concentrations that have attracted the interest of mining companies for decades. They contain not just manganese but cobalt, nickel, copper, and rare earth elements that are essential to modern technology and currently difficult and expensive to extract. There are also massive sulfide deposits at hydrothermal vent sites, concentrations of copper, zinc, lead, gold, and silver that formed as the mineral-rich vent fluids cooled and precipitated their contents. On the exposed seafloor, all of this would be accessible. Not buried under kilometers of water, not requiring specialized deep-sea mining equipment, not subject to the international legal complexities of seabed mining in international waters. Just there, lying on the surface of newly formed land, waiting to be picked up. Future civilizations, adapted to a drier, harder, more extreme world, would find in the former ocean basins a geological inheritance of almost unimaginable value. The raw materials for whatever technology and industry had survived the transformation would be present in concentrations that the terrestrial mineral deposits could never match. The bones of the old ocean, rich with everything the sea had spent millions of years collecting, available at last. There is something quietly ironic in that. The ocean, which had given the world so much for so long, oxygen and rainfall and climate moderation and food and the currents that made navigation possible, leaving behind, even in its absence, one final gift. Locked in the sediment and the rock and the slow accumulations of the deep-sea floor, a world changed beyond recognition, but not, perhaps, entirely emptied. There is a photograph, you may have seen versions of it, taken from the window of a plane flying over what used to be the Aral Sea in Central Asia, where there was once a vast body of water, the fourth largest lake in the world. There are now rusted ships sitting in the middle of a desert, just sitting there, kilometers from any water, listing slightly in the sand, their hulls oxidized to shades of orange and brown, surrounded by nothing but dry earth and scrub in every direction. The sea left, the ships stayed, and now they sit there as monuments to a transformation that happened within living memory, a reminder that the landscape is not as permanent as it looks, and that the things we build in relation to water can outlast the water itself by a very long time. That image, those ships in the desert, is a small preview of what the retreating ocean would eventually do to the coastlines of the world. Except instead of a few dozen vessels on a dried-up lakebed in Uzbekistan, It would be the port infrastructure of entire civilizations, left stranded as the sea pulled back across decades and centuries and millennia. Think about what a port city actually is. It is a place built around a relationship with the water. Everything about it, the docks and the harbors, the breakwaters and the channels, the warehouses along the waterfront, the roads and railways that lead down to the quayside, all of it organized around the fact that ships arrive here and ships depart from here, and the sea is right there at the edge of the city, accessible, present, the reason the city exists in its particular location at all. As the sea level dropped, that relationship would begin to strain. The harbor would need to be dredged more frequently to stay navigable. The docks would need to be extended. The channels would be deepened and lengthened. For a while, engineering could compensate. Humanity has always been remarkably good at building its way around inconvenient geography. But there are limits to what engineering can do when the problem is not a difficult coastline but a retreating one. When the sea is not just challenging to navigate but is actually moving further away, year by year, the infrastructure designed to meet it would eventually become inadequate no matter how much it was extended and modified. And then the city would find itself no longer coastal. Not dramatically, not with any single moment of loss, but over generations. The waterfront gradually retreating, the old port district becoming inland, new port facilities built further out toward the new shoreline, then those becoming inland too. The original harbor, where the city had begun, sits hundreds of kilometers from the sea, still there, still recognizable in its layout, but no longer a port, just a place where the port used to be, its architecture still telling the story of what it was built for, even though what it was built for was gone. Every major coastal city on Earth would go through some version of this. The timescales would vary. Some coastlines would retreat faster than others, depending on how shallow the adjacent seafloor was and how quickly the water level dropped. But the direction would be the same everywhere. London and New York and Shanghai and Mumbai and Sydney, all of them built around their relationship to the sea, all of them eventually finding that relationship stretched past the breaking point. People would move, of course. They always do. The new coastline would attract new settlement, new ports, new cities built around the waterfront that existed now rather than the one that used to exist. But the old cities would remain, too large, too established, too full of infrastructure and history to simply be abandoned. And they would adapt to their new inland status, becoming something different from what they had been. Trading hubs rather than ports. Transportation centers. Places where the memory of the sea was preserved in street names and architecture and the shape of old harbors that no longer held water. And the land between the old cities and the new coastline, the exposed continental shelf, the former seabed, would slowly be settled and transformed. Not quickly. That land would take time to become habitable. The salt would need to be leached out by what rain remained. The sediment would need to consolidate. The toxic chemistry of some exposed seabeds would need to be addressed. But over generations, people would move onto it. Farm it where farming was possible. Build on it. Road networks would extend across what had been the ocean floor, connecting the old coastal cities to the new shoreline in long, straight lines across remarkably flat terrain. The islands would present a different kind of transformation. Islands are, by definition, pieces of land surrounded by water. Their identity, ecological, cultural, often political, is built around that separateness, that isolation in the sea. Island ecosystems develop their distinctive character precisely because they are islands, cut off from the mainland, their species evolving in isolation. Island cultures develop their distinctive character for similar reasons. The sea that separates an island from a continent is not just geography. It is the condition that made the island what it is. As the ocean level dropped, the sea around many islands would become shallow and then disappear. Islands that had been surrounded by deep water would find themselves surrounded by shallower water, then very shallow water, then by the beginnings of exposed seafloor, and eventually, as the process continued, by land. The island would still be there, still elevated above the surrounding terrain but no longer an island, connected to the nearest continent or to other former islands by land bridges of exposed seabed. The ecological consequences would be profound. Species that had evolved in isolation on oceanic islands over millions of years, the extraordinary biodiversity of places like Madagascar or the Galapagos or New Zealand, which owe their unique character entirely to their long isolation, would suddenly face connection to the mainland and everything that came with it. Continental species moving onto the new land bridges and reaching the former islands. Competitive interactions that island species had never encountered and had no defenses against. The same process that happened when humans first brought rats and cats and pigs to oceanic islands, but on a far larger scale and driven not by human introduction but by the geography itself changing. New land bridges would also open up migration routes that hadn't existed for millions of years, or in some cases had never existed at all. Animals that had been separated by ocean for geological eons would find themselves neighbors. The consequences of that, played out over thousands of years of ecological adjustment, would be one of the most extraordinary episodes in the history of life on Earth. The birds would feel the change in a different way. Many of the world's migratory bird species make crossings that depend on specific conditions, specific stopover points, specific coastlines to navigate by, specific weather patterns that make the crossing manageable. The bar-tailed godwit flies non-stop from Alaska to New Zealand, a journey of over 11,000 kilometers across the Pacific, navigating by the stars and the Earth's magnetic field and some internal map that science is still working to fully understand. Arctic terns make a round trip from pole to pole every year. Hundreds of species navigate by coastlines, island hopping across what are currently ocean gaps that would not be crossable over land. As the coastlines moved and the ocean shrank, those routes would be disrupted. Stopover points would shift or disappear. The weather patterns that migratory birds rely on would become less predictable. Some ocean crossings would shorten as new land appeared, making previously impossible routes suddenly feasible. Others would lengthen as the geography changed. Some species would adapt. Evolution always finds a way, given enough time and enough survivors. Others would not adapt fast enough, and their ancient routes, flown for millions of years, would simply become obsolete. There is something melancholy about that particular loss. The idea of a species that has navigated half the planet every year for millennia, suddenly finding that the map no longer matches the territory. The freshwater would become everything. In a world where the oceans were retreating and rainfall was declining and rivers were failing, the remaining sources of liquid freshwater would become the most valuable resource on the planet. More valuable than oil had ever been. More contested than any territory in human history. Because without fresh water, nothing else matters. Not the mineral wealth of the exposed seabed. Not the new land opened up by the retreating coastlines. Not any technology or adaptation that human ingenuity could devise. Life requires water, and water is becoming scarce. The glaciers and polar ice caps, already diminishing, would be managed with a care bordering on reverence. Whatever ice remained would be treated as a strategic reserve, the equivalent of a national treasury, but for something more fundamental than money. Nations with glaciers would find themselves holding an asset that other nations needed desperately. The geopolitics of ice would become one of the defining tensions of the age. The deep lakes, those that remained fed by sufficient groundwater or snowmelt to stay full, would be similarly contested. Lake Baikal in Siberia, the deepest lake in the world, holding about 20% of the world's unfrozen surface freshwater. The Great Lakes of North America, the Caspian Sea already shrinking. These bodies of water, and others like them, would become the centers of human settlement in a way that coastlines had been in the Old World. Cities would consolidate around them. Political power would organize itself around access to them. Wars would be fought over them, or the threat of wars would shape the diplomacy of every civilization that had any connection to them. And the water that remained would be used with an intensity of care that the old world, the world of full oceans and reliable rainfall, would have found almost incomprehensible. Nothing wasted, nothing allowed to evaporate unnecessarily. Every drop recycled through systems of increasing sophistication, cleaned and recirculated and used again. Moisture drawn from the air itself, in the places where the air still held enough humidity to make that worthwhile. Condensation collected from any surface where temperature gradients made it form. Societies would organize themselves around water in the way that earlier societies had organized themselves around food production. Every technology, every social structure, every political arrangement ultimately in service of managing the resource that everything else depended on. The engineering would become extraordinary over time. Underground aquifers sealed against evaporation. Covered reservoirs in which the air above the water was managed to reduce losses. Distribution networks of a complexity that would make the water infrastructure of the current world look rudimentary. And there would be those who thought bigger, much bigger, over very long timescales. With enough technological development and enough desperation to drive it, there might be attempts to address the problem at its source, to slow or stop the escape of water vapor from the upper atmosphere, to build some kind of barrier or intervention that reduced the rate at which hydrogen was being lost to space. Whether such a thing was physically possible, whether the engineering required was achievable by any civilization that still existed on the drying earth, is uncertain. But the impulse would be there, the same impulse that has always driven human beings to attempt interventions in natural processes that threaten their survival. The attempt to hold back the tide, in the most literal sense imaginable. Perhaps enormous underground reservoirs, not just cisterns or aquifers but true underground oceans, sealed environments where water was stored in quantities large enough to buffer the loss, insulated from the heat that would evaporate it, protected from the atmosphere that would carry it away. The idea sounds fantastical, but so would the concept of modern water treatment infrastructure to someone from a few centuries ago. Necessity has a way of making the fantastical into the achievable. On the surface of the new dry world, old things would be visible in strange new contexts. The underwater internet cables that currently carry the vast majority of the world's digital communications, thin bundles of fiber optic cable lying on the ocean floor, spanning entire ocean basins, connecting continents in lines that most people never think about even as they depend on them constantly, would eventually lie exposed on the surface of the former seafloor, stretching across the dry basins in the paths they had been laid, still tracing the routes between what used to be continents and what were now just different parts of the same continuous landmass. They would look, to anyone crossing the former ocean floor, like lines drawn across the landscape, slightly elevated above the sediment, running in long, gentle curves toward distant horizons. Old highways of a different kind of communication. Navigational aids in their own right, in a place with very few landmarks, since following a cable would eventually lead you to where it had once made landfall. Future travelers crossing the former ocean basins might use them as guides, the same way travelers in other eras had followed rivers or coastlines or the stars. And those travelers would be carrying maps. Old maps. Maps from the world before the retreat, showing the ocean as it had been. The depths marked in fathoms, the currents indicated with arrows, the sea lanes marked in the lines that ships had followed for centuries. Those maps, in the New World, would be something like what topographic maps are to hikers today, guides to the terrain showing elevation and gradient and the location of features, except the features they showed were the former seafloor rather than a mountain range. The Mariana Trench, marked on old nautical charts as a depression of extreme depth, would now be a canyon to be avoided or descended carefully. The mid-ocean ridges, shown on old oceanographic maps as mountain ranges beneath the sea, would now be mountain ranges above the sea, the same geography, the same contour lines, now referring to things you could see rather than things you could only measure by echosounder. A sailor's chart of the Pacific, drawn in the 20th century, would become a hiker's map of the former Pacific Basin. The soundings taken by research vessels over a century of oceanographic work would become elevation data for the new land. There is something deeply strange and quietly beautiful about that continuity. The same information, recorded for one purpose, becoming useful for an entirely different one. The charts of the old ocean became the maps of the new desert. The measurements of depth became measurements of height. The sea lanes became the roads of a world that no longer had a sea. And somewhere, in the archives of whatever civilization survived and maintained their connection to the past, there would be the old maps. Not just the navigational charts, but the maps that showed the world as it had once been. The full blue expanse of the Pacific, the breadth of the Atlantic, the shapes of coastlines that no longer existed in those forms. Maps from an age when most of the planet was covered in water. Maps that showed a world almost unrecognizable from the one that the people looking at them inhabited. They would look at those maps the way we look at maps of Pangaea, the ancient supercontinent that broke apart 200 million years ago, before any of the current continents existed in their present forms. With a kind of awe at the difference, with the understanding that the world has always been changing, and that the world they knew was not the world that had always been, and that the world that would come after them would be different again. The ocean on the old maps would look like a legend, something from mythology, something almost too vast and too complete to have been real. But it was real. It had been there, blue and enormous and full of life, covering most of a planet, shaping every climate, sustaining every breath. For billions of years it had been there, and the people of that future world, looking at the old maps in the light of a drier sun, on a planet that had forgotten the sound of waves, would know that it had been real, that it had existed, that once the world had been mostly water, and that once it had been enough. There is a concept in climate science called albedo. It is simply a measure of reflectivity, how much of the sunlight that hits a surface gets bounced back into space rather than absorbed. Snow and ice have very high albedo. They are white, and white reflects light. Dark rock and soil have low albedo. They absorb light, and the energy of that light becomes heat. The ocean sits somewhere in between, depending on the angle of the sun and the state of the surface, but in general, water reflects a significant portion of the sunlight that hits it, particularly when the sun is low on the horizon and the light is coming in at a shallow angle. This matters enormously for the planet's energy balance. The Earth is not simply heated by the sun. It is heated and reflected in a complex balance that determines how warm the surface gets and how that warmth is distributed. Change the reflectivity of the surface, and you change the balance. You change how much energy the planet retains. You change the temperature, and the ocean covers 71% of the Earth's surface. As the oceans retreated, the seafloor they left behind would be dark. Not uniformly dark. Some exposed seabed would be pale with salt, and those regions would reflect well. But much of the former ocean floor, particularly the deep seafloor of basaltic rock and dark organic sediment, would be among the least reflective surfaces on the planet. Where there had been water reflecting sunlight back into space, moderating the energy budget of the planet, there would now be dark rock and dark sediment, absorbing that energy instead, turning it into heat, keeping it. The effect would be gradual, as everything in this story is gradual. But it would be cumulative and self-reinforcing. A more dark surface means more heat absorbed, means higher temperatures, means more evaporation of whatever water remains, means more water lost to the atmosphere, means more dark surface exposed. A feedback loop, tightening slowly over time, each turn of the cycle pushing the planet a little further along the same path. This is already a mechanism we understand, in miniature, from what's happening today. The Arctic sea ice is melting, and as it does, the dark ocean water beneath it is exposed, and that dark water absorbs more heat than the ice did, which warms the water further, which melts more ice. It's one of the reasons the Arctic is warming faster than anywhere else on Earth. The same principle, operating at a much larger scale over a much longer time scale, would play out across the retreating oceans of the world we're imagining. The planet would be getting warmer, not from any external change. The sun would be doing what it always does, providing the same energy it always has. But the planet's ability to send that energy back would be diminishing, and the result would be accumulating heat. More than the world had experienced in a very long time. There is a famous quality of water, the fact that it reflects light back into space. But there is another quality, less often discussed in everyday conversation, that is just as important. Water absorbs carbon dioxide. The oceans are, right now, one of the planet's primary carbon sinks. They pull CO2 out of the atmosphere and dissolve it into seawater, where it eventually becomes part of the chemistry of the ocean and, over long periods, is incorporated into the shells and skeletons of marine organisms and sequestered in the seafloor. The ocean has been performing this service for hundreds of millions of years, and it is one of the reasons the Earth's atmosphere has remained within the range of conditions that support complex life. As the oceans shrank, that carbon-absorbing capacity would shrink with them. Less ocean surface, less dissolved CO2, more of it remaining in the atmosphere where it does what CO2 in the atmosphere does. Traps heat, prevents it from radiating back into space, warms the planet. The greenhouse effect would intensify, not because of any industrial activity, but simply because the mechanism that had been counteracting it was going away. And then, from beneath the retreating seafloor, something worse. On the ocean floor, in the cold and pressure of the deep sea, there exist enormous deposits of a substance called methane clathrate, sometimes called methane hydrate or fire ice. It is methane gas locked inside a crystalline structure of water molecules, stable only under specific conditions of cold temperature and high pressure. The deep seafloor has both, which is why these deposits exist there in such quantities. They are vast, containing, by some estimates, more carbon than all of the world's known coal, oil, and natural gas reserves combined. They have been sitting quietly on the ocean floor, stable and inert, for millions of years. As the water above them retreated, the pressure would decrease. As the temperature of the exposed seafloor increased, the cold that kept the clathrate stable would diminish, and the methane, freed from its crystalline prison, would bubble up. Not all at once. The deposits are spread across enormous areas of seafloor and would thaw at different rates. But over time, over the long centuries and millennia of the ocean's retreat, enormous quantities of methane would be released into the atmosphere. Methane is a potent greenhouse gas, significantly more powerful than carbon dioxide over short timescales at trapping heat. The release of these frozen deposits would add to the warming that was already underway from the lost albedo and the reduced carbon absorption. More heat, higher temperatures, a planet running hotter than it had in a very long time and getting hotter still. The atmosphere itself would be changing in a more fundamental way too, though on a timescale even longer than everything else in this story. The hydrogen that had been escaping into space since the beginning of this process, broken out of water molecules by photodissociation, light enough to drift beyond Earth's gravity, would have been taking the atmosphere with it molecule by molecule. Not quickly, not in any way measurable over a human lifetime, or even over many human lifetimes. But over millions of years, the cumulative loss would add up. The atmosphere would gradually thin. The blanket of air that surrounds the planet and protects it from radiation and maintains the pressure that liquid water requires would slowly become less substantial. This would eventually matter enormously. Liquid water cannot exist on a planet's surface without sufficient atmospheric pressure. Mars lost most of its water not only because of a weakened magnetic field that allowed solar wind to strip its atmosphere, but because once the atmosphere thinned enough, the pressure dropped below the threshold at which water can remain liquid. It either evaporates or freezes, with nothing in between. Earth is a long way from that threshold, and would remain so for an extremely long time. But the direction of travel, in the very long run, would be the same. And as all of this changed, the albedo, the carbon, the methane, the atmosphere, other things would change too. Quieter things, subtler things. Things you might notice if you were paying attention without necessarily understanding what they meant. The tides would weaken. Tides are caused by the gravitational pull of the moon and to a lesser extent the sun, acting on the water of the oceans. The moon doesn't just pull the ocean toward it. It creates a bulge of water that travels around the planet as the Earth rotates, generating the rhythmic rise and fall of sea level that has shaped coastlines and influenced navigation and governed the lives of coastal communities for as long as human beings have lived near the sea. As the volume of ocean water decreased, the moon's gravity would have less water to work with. The tidal bulge would be smaller. The tides would be lower, not dramatically at first, but measurably over long periods. The great tidal ranges that currently exist in places like the Bay of Fundy, where the tides can rise and fall by more than 15 meters, would diminish. The coastlines would lose one of their most characteristic features, that twice-daily rhythm of advance and retreat that is so fundamental to coastal ecology and human maritime culture that it is almost invisible precisely because it has always been there. The moon itself in the sky would look different, not in its shape or its motion. Those are governed by its orbit, which the loss of Earth's oceans would not affect. But one of the most striking things about a full moon over a calm sea is the reflection. The path of moonlight rippling across the water toward you, the way the ocean takes the moon's pale light and spreads it across the surface in a shimmering column. The ocean does this because it is a liquid, and liquid surfaces reflect light in that particular beautiful way. As the oceans shrank, that reflection would shrink with them. The moon, seen from a planet with less water on its surface, would appear dimmer in terms of how much of its light was returned to the sky. The night landscapes that had always been lit by the combination of moonlight and sea reflection would grow darker. The moon would still be there, still moving through its phases, still pulling at what water remained. But its light would land on dark sediment rather than open sea, and the world at night would be a little more shadowed than it had been. The sunsets, though, might be extraordinary. Sunsets are colored by the way sunlight interacts with the atmosphere, specifically with the particles and molecules in the air, which scatter different wavelengths of light in different ways. Water vapor and clouds and dust all affect the color and texture of a sunset. In a world with less atmospheric moisture, with fewer clouds, with drier and clearer air, the sunsets would change character. The hazy, diffuse colors produced by humid air would give way to something sharper, crisper. The sky at the horizon would be a more saturated blue during the day, transitioning through colors that were cleaner and more vivid as the sun descended. Deep oranges and reds in an atmosphere that was clear enough to let those wavelengths travel further without being scattered away. It is one of the strange gifts of this transformation, that as the world becomes drier and harsher, the sky might become more beautiful in certain specific ways. The clarity of low humidity air produces sunsets of a quality that humid regions rarely see. Desert sunsets in the current world are often spectacular for exactly this reason. The whole sky of the future world might have something of that quality, vast and clear and deeply colored at the edges of the day. And the nights, above the former ocean regions, above the enormous dry basins that had once been the Pacific and the Atlantic and the Indian Ocean, the sky at night would be clearer than human beings had ever seen it from those latitudes. Currently, much of the light that reaches the ocean surface and is absorbed by the water creates evaporation, which creates humidity, which creates haze in the lower atmosphere. The ocean keeps the air above it moist, and moist air, even without clouds, reduces the clarity of the night sky in subtle ways. On the dry former seafloor, the air above would be extraordinarily dry. No ocean evaporation feeding moisture into the atmosphere. No humidity haze, just clear, cold, dry air between the observer and the stars. The Milky Way, which is invisible from most of the currently populated world due to a combination of light pollution and atmospheric moisture, would blaze overhead in the dry air of the former ocean basins. Stars that had been faint and wavering when seen through humid air would be sharp and steady. The sky would look the way it looks from the highest, driest mountains, from places like the Atacama Desert, where some of the world's best astronomical observatories are located precisely because the air is so dry and clear. In the midst of everything being lost, the sky would be given back. From space, though, the view would tell a different story. Earth, seen from a distance, has always been blue. That is the color it appears from space. The blue of the ocean covering most of its surface, broken by the white of clouds and the brown and green of continents. It is one of the most striking things about our planet as seen from outside it, that overwhelming characteristic blue that has made it, in every photograph taken from space, look almost impossibly vivid and alive. As the oceans shrank, that blue would fade. The brown and gray of the exposed seafloor would spread across what had been the great ocean basins. The white of salt flats would appear in broad swaths. The green of whatever vegetation survived on the continental masses would remain in places, but diminished, drying at its edges. And the cloud cover, those great swirling patterns of white that wrap the planet and are one of the things that make it look most dynamic and alive from a distance, would thin. Fewer clouds, forming less frequently, covering less of the sky at any given moment. The planet would look drier from space, more exposed, less wrapped in weather. The blue would retreat toward whatever ocean basins still held water, a shrinking patch of color on a world that was gradually showing more of its bones. It would still be a planet, still orbiting the sun, still moving through space in its ancient path, still turning on its axis, still producing sunrises and sunsets and seasons. But it would look from a sufficient distance like something was wrong, like the vitality had gone out of it, like the thing that had made it unmistakably, vibrantly, recognizably alive was slowly diminishing. And from the surface, looking up at a sky that was clearer than it had ever been, at stars that blazed in the dry night air, at sunsets that burned in colors that the old humid world had never quite achieved, at a moon that crossed the sky without its reflection on any sea, you might have the feeling of a world that had become, in its drying, paradoxically more transparent, more exposed, as though the ocean had been a kind of covering, a kind of softness, and without it the planet was showing something truer and harder and more ancient underneath. Not more beautiful exactly, not less beautiful exactly, just different, starkly, irreversibly, completely different. The blue planet becoming something else, slowly, silently, under a sky full of stars. We are deep in the future now. Not the near future or even the distant future in the way science fiction usually means it. Not centuries from now, not millennia. We are speaking of timescales so vast that they don't have much meaning in terms of anything human civilization has so far experienced. The kind of time in which entire mountain ranges rise and are eroded flat. The kind of time in which the continents themselves have moved. The kind of time that makes the whole of recorded human history look like the last second of a very long day. And in that time, the oceans have continued their retreat. Slowly, always slowly, but without pause, without reversal, the water has been going. And now we are approaching the end of something that has been continuous on this planet since before any complex life existed. Something so ancient and so foundational that it is difficult to think of Earth without it. The ocean is almost gone. From space, if there were eyes to see it, if there were any vantage point from which the whole planet could be observed, Earth would be nearly unrecognizable. The blue that has always defined it, that overwhelming color that made it look like a jewel against the black of space, would be gone. Not faded gradually into something paler, but genuinely, substantively gone, replaced by the colors of rock and sediment and salt. Brown and gray and white and ochre, the colors of a dry world, spread across the vast basins that the oceans had vacated over their long retreat. The continents would look enormous, because in a sense they would be. Not because the landmasses themselves had grown, the tectonic plates would still be roughly where they always were, but because the ocean floor surrounding them had become land. The vast abyssal plains, the mid-ocean ridges, the continental slopes and shelves. All of it exposed now, all of it dry, all of it adding its area to what could be seen from above as continuous land surface. The planet would look like it was mostly land because it would be mostly land. The visual balance that had always defined Earth, that sense of a world where water dominated and land was the exception, would have inverted completely. What remained of the ocean would be visible from space as patches. Darker blue against the brown. Smaller than you would expect, smaller than seems possible for something that was once so vast. Tucked into the deeper basins, the places where the ocean floor dipped lowest and the retreating water had pooled last. From a distance, they might look like large lakes. From the surface, standing at their shores, they would still feel like the sea. The water would still move, still smell of salt, still catch the light in the way that water always does. But the horizon would be closer than it used to be. The depth would be less. And in every direction beyond the shoreline, instead of more ocean, there would be the dry expanse of what had been the ocean floor. The atmosphere above the remaining water bodies would do something strange in certain conditions. As the last seas evaporated, slowly, inexorably, their surfaces releasing moisture into the surrounding air, there would be times and places where that moisture, meeting the cold, dry air above the basin walls, would condense rather than disperse. Fog. Not the coastal fog of the old world. Not the sea fog that rolls in off warm water and blankets a shoreline in gray, but something denser and more enclosed. Thick banks of fog filling the floors of former ocean basins, pooling in the deepest valleys, hugging the surface of the remaining water and spreading outward onto the dry surrounding seafloor where the moisture cooled and thickened into something you could almost see through but not quite. In the mornings, in those basins, you might not be able to see the water at all. Just a white interior, a fog so thick it seemed solid, filling the low ground from wall to wall. And then, as the sun climbed and the temperature rose, the fog would lift and retreat, pulling back toward the water it had come from, thinning as it went, until by midday there was just the flat blue surface of the last sea, clear and still, the fog gone until the next night brought the cold back. There would be life in that water, changed, adapted, strange by the standards of any ocean that had preceded it, but alive. Life is, among other things, extraordinarily persistent. It has survived asteroid impacts that killed the majority of species on Earth. It has survived ice ages that covered most of the planet in glaciers. It has survived volcanic episodes that filled the atmosphere with ash and poisoned the oceans with acidity. Every time the conditions changed dramatically, some things died and other things adapted, and life continued, altered but unbroken. The increasingly saline, increasingly warm, increasingly shallow waters of the last seas would be challenging environments. The salt concentration would be rising as the water volume decreased, because the salt had nowhere to go. It didn't evaporate, it didn't escape. Concentrated. Waters that had once been as salty as the current ocean, about 3.5% salt, would become saltier. Much saltier in some places, the kind of hypersaline environment that most marine life could not tolerate. But some things could. Brine shrimp live in salt lakes where the salinity is many times that of the ocean. Halophilic bacteria thrive in conditions that would pickle most organisms. The salt flats of existing hypersaline lakes support their own microbial ecosystems, invisible to the naked eye but genuine and persistent. As the last seas concentrated, the organisms that survived would be the ones already adapted to or capable of adapting to those extreme conditions. Smaller, simpler in some ways, more chemically resilient. The large and complex marine ecosystems of the old world would be long gone. What remained would be something more fundamental, life operating closer to its basic principles, finding ways to persist in conditions that seemed designed to exclude it. Some larger animals might make it further than you'd expect. Creatures that could tolerate elevated salinity, that could handle the temperature swings of shallow water, that were small enough and adaptable enough to survive in habitats that were a fraction of the size they had once occupied. Over thousands of generations in isolated water bodies, the fragmented remnants of the last ocean, separated from one another by dry land. Some of these survivors might become something genuinely new. Evolution, given isolation and pressure and time, produces novelty. The organisms that lived in the last waters of Earth would not be the organisms that had lived in the full ocean. They would be their descendants, changed by necessity into something the old ocean would barely have recognized. The underground would matter more than the surface. As the surface water became scarcer and more extreme, the focus of both life and human civilization would shift downward. Groundwater, water stored in aquifers beneath the surface, filtered through rock and held in porous geological formations, had always been important, but now it would be essential. The water table, wherever it remained, would be the most important thing in the landscape. Communities would organize around it. Wells would be the centers of human settlement the way rivers had been in an earlier age. The depth of the water table, the quality of the water it held, the rate at which it could be sustainably withdrawn, these would be the defining variables of where life was possible. In the deeper aquifers, far below the surface, something remarkable would be continuing that most surface observers would never know about. Microbial life. Bacteria and archaea living in the water-saturated rock hundreds of meters down, sustaining themselves on chemical energy rather than sunlight, completely independent of what was happening at the surface. These subsurface microbial communities are real. They exist in the current world, discovered by scientists drilling deep into the Earth's crust, and they constitute a significant fraction of the total biomass of life on the planet. They are slow-metabolizing, ancient, and astonishingly resilient. As the surface became increasingly inhospitable, these deep communities would persist, unaffected by the retreating ocean, unconcerned with the changing atmosphere, oblivious to the drying of the surface world, just living, as they had always lived, in the dark and the wet of the deep rock. If there was a last redoubt of life on Earth, it would not be at the shore of the last sea. It would be underground, in the water-bearing rock, in communities of microorganisms that had no awareness of the world above them and no need for it. The surface, meanwhile, would be consolidating around whatever water remained accessible. The last coastlines would be unlike any that had come before. Not the gently sloping beaches of a full ocean, not the dramatic cliffs where continental shelves dropped away, but the shores of inland seas, hemmed in by the towering walls of former ocean basins, surrounded by the vast dry expanse of the seafloor that the water had vacated. Standing at the shore of one of these last bodies of water and looking out across it, you would still see an horizon, still see waves, still feel the particular quality of air that exists near a body of water. Slightly moister, slightly cooler, carrying the faint mineral smell of salt. But looking back, away from the water, you would see the walls of the basin rising around you. The former continental slopes, now exposed, climb toward the distant rim where the old land surface began. And beyond those walls, invisible from the shore, the immense dry world that stretched in every direction. The former ocean floor, now desert, now salt flat, now dune field, now the bare rock of the mid-ocean ridges standing in open air. The coastlines of the last seas would be in constant motion. As the water level continued to drop, year by year and decade by decade, the shoreline would migrate inward. Communities built at the water's edge would find themselves inland within a generation. There would be no point in investing heavily in permanent coastal infrastructure, because the coast would not stay where it was. People would move constantly, following the water, making temporary settlements that were always understanding their own impermanence. A society organized around the expectation of continuous retreat. Animals would do the same, Whatever species had survived to this point, adapted to the salinity and the heat and the shrinking habitat, would follow the retreating waterline with the same driven urgency that any animal follows the resource it cannot live without. Migrations that had once been seasonal would become permanent. The movement wouldn't stop because the water wouldn't stop moving. Always inward, always less, always another kilometer further from where it had been. The world by this point would be, in every visual sense, a desert world. Not a world with deserts in it. Not a world where dry regions existed alongside wetter ones, balanced against each other in the larger pattern of climate and circulation. Simply a desert world, the way Mars is a desert world, the way the images from rovers on other planets show landscapes of rock and dust and silence with no softening, no green, no water visible anywhere except as frost or vapor at the extremes of temperature. Except that here, in this world, tucked into the deepest valleys of the former ocean basins, there would still be water. Not much. Not enough to cover what it used to cover. Not enough to do what it used to do for the planet's climate and chemistry and biology. But real water, liquid water, is still present on the surface, which makes this world something different from Mars, something more than a dead planet. Still just barely a living one. The deep valleys would be the last strongholds. The places where the ocean floor dipped lowest, the remnants of the deepest basins, the final depressions that the retreating water filled last and would empty last. In those valleys, the water would remain longest. Hypersaline, warm, shallow by the standards of the old ocean, but wet. Still wet in a world that was almost entirely dry. And around those valleys, in the margins where the moisture from the water reached the surrounding land, there might still be something growing. Sparse, adapted, unlike anything in any botanical record from the age of the full ocean, but alive. Salt-tolerant vegetation clinging to the lowest ground. Microbial mats at the water's edge, doing what microbial mats have done since the beginning of complex life on this planet. The thin edge of biology, persisting because biology persists. The sky above it all would be extraordinarily clear. Dry air, minimal cloud cover, the atmosphere thinner than it used to be. The stars at night would be sharp and numerous and close-seeming, as though the removal of so much intervening moisture had brought the universe a little nearer. The sun during the day would be harsh and direct, with nothing to filter it. Seen from above, from high enough to take in the whole basin at once, it would be a strange and austere beauty. The last water of Earth, dark in the deep valley, surrounded by the white and brown of the dry world, under a sky so clear it almost hurts to look at. Small, precious, real. The planet holding on to the last of what it had been. The water that had covered most of its surface for billions of years now reduced to this. A pool in a valley, a remnant, a memory made liquid. Still reflecting the sky. Still moving in the wind. Still improbably home. We have come a long way from the beginning of this story. Do you remember where we started? The tropical seas, warm and blue, evaporating just a little more than usual. The change was so small that no one noticed. The first invisible shift, quiet as a thought, in a world that looked exactly like it always had. The waves are still coming in. The tides are still going out. The ocean is still vast and full and ancient, covering most of a planet that had no idea what was beginning. That was a long time ago, an almost incomprehensible time ago. The kind of time in which everything changes, not once but many times, in which the very rock beneath your feet has moved and folded and risen and fallen, in which the species alive at the beginning would be as alien to the species alive at the end as creatures from another world entirely. And now we are here, at the end of the water, at the end of the ocean, at the final chapter of something that began before complex life existed on this planet and is only now, after billions of years, coming to a close. The Earth is almost dry. Not entirely, not yet, but close enough that the difference between now and the end is a matter of degree rather than kind. The world has already become what it will be. The transformation is essentially complete, even if the last traces of water have not yet surrendered. And the planet itself is still responding, still adjusting, still moving in ways that take millions of years to become visible but are happening all the same, the slow mechanical processes of geology continuing regardless of what has been lost from the surface above. The ocean has weight. This is obvious when you think about it. Water is dense, and the ocean is enormous, and the combined mass of all that water pressing down on the ocean floor has been a significant force on the Earth's crust for as long as the ocean has existed. The crust beneath the ocean has been compressed, pushed down slightly by the load above it, in the same way that thick ice sheets push down the land beneath them, a process called isostatic depression. And just as the land rebounds when the ice melts, as Scandinavia and Canada are slowly rising today, still recovering from the weight of the glaciers that melted 10,000 years ago, the ocean floor would rebound as the water above it disappeared, slowly, imperceptibly at first, but measurably over the long centuries and millennia of the ocean's retreat. The former seafloor would be rising, not dramatically, not quickly, but upward, the crust responding to the removal of a load it had been carrying for hundreds of millions of years, flexing back toward a position it hadn't occupied since before the ocean existed. In some places, this rebound would be enough to affect the topography significantly. The deep basins would become slightly shallower, not just because the water was gone, but because the floor itself was rising to meet the vanished surface. And in other places, the redistribution of stress in the crust, the changing balance of forces as the ocean's weight was removed, would have a different effect. The crust is not uniform. It is fractured and faulted, divided into plates and blocks and zones of weakness, and the pressure of the ocean on top of it had been part of what kept those zones stable. Remove the pressure and the stability changes. Faults that had been held in a certain configuration by the weight above them would experience new stresses. The rate of seismic activity in former ocean regions would shift. Volcanoes that had been submarines, that had vented their energy into the water above them for millions of years, would now be venting into the open air, and some of them would become more active as the confining pressure of the ocean was removed. The deep cracks in the former seafloor would breathe. This is one of the stranger images of the final world, the dry ocean basins venting. Not dramatically, not with the catastrophic eruptions of major volcanoes, but steadily, through the fractures and fissures and hydrothermal systems that had always existed along the tectonic boundaries of the ocean floor. Gases rising from the Earth's interior, sulfur dioxide, carbon dioxide, hydrogen sulfide, steam from residual heat, and any remaining groundwater deep in the rock, emerging from vents scattered across the vast dry basins, creating strange landscapes of steaming ground and mineral-crusted openings in the otherwise featureless expanse of former seafloor. In places, the smell would be extraordinary. Sulfurous, mineral, ancient. The breath of the Earth's interior. The chemistry of the deep mantle expressed at the surface in ways that the ocean had previously absorbed and dissolved and moderated. Without water to receive it, that chemistry would just be there, in the air, raw and direct. Strange plumes of vapor rising in the clear, dry atmosphere, visible for kilometers across the flat basin floor, the only vertical elements in a landscape that was otherwise relentlessly horizontal. And in the deepest parts of that landscape, in the remnants of the deepest trenches and basins, people might be living. It sounds unlikely, but think about what the deep trenches would offer in a world of extreme surface temperatures and scarce resources. Depth means coolness. The further you go below the surface, the more insulated you are from the temperature extremes above. The walls of a deep trench would provide shade. The geology of the former ocean floor would provide access to minerals and geothermal energy. The remaining pockets of groundwater would be most accessible at depth, where the water table, whatever remained of it, was closest to the surface. Human beings have always built their civilizations in the places that offered the best combination of resources and protection. In the old world, that meant coastlines and river valleys. In the world of the dry earth, it might mean the floors of ancient ocean trenches. Deep, shaded, cooler than the surface, closer to the water table, sheltered from the wind that scoured the open basins. Cities built downward rather than upward, into the rock and the relative cool, in the deepest surviving geography of a world that had run out of most other options. The last ocean, wherever it persisted, would be the center of everything. Whatever civilization had adapted to this world would organize itself around the remaining water with an intensity that no previous human culture had ever needed to. The final sea, concentrated, saline, warm, reduced from its former self in every dimension, would nonetheless be the most valuable thing on the planet. The last source of liquid surface water. The last functioning piece of the hydrological system that had sustained life for billions of years. In the very deepest basin, in the lowest point of what had once been the ocean floor, the water would persist the longest. Held there by gravity, concentrated by evaporation into something very different from the ocean it had come from. Dense with salt and minerals, barely resembling seawater in its chemistry. But liquid. Still liquid. Still real. This final body of water, enormous by the standards of anything that currently exists on Earth's surface outside the oceans, would be tiny by the standards of what the ocean had been. A remnant, a residue, but it would be the last place on the surface of the Earth where water moved and reflected light and supported whatever strange, adapted, salt-tolerant life had made it this far. The last coastline in the world, migrating inward year by year, the water retreating to its final center. And then, eventually, one day, the last water would be gone too. Evaporated. Escaped. The hydrogen finally gone beyond the reach of gravity, the oxygen locked away in the rock. The surface dry from pole to pole. When that happened, if that happened, Earth would be something that it had not been since its earliest formation billions of years ago. A dry rock, a planet without a surface ocean, without the thing that had made it, for all the billions of years of its middle life so extraordinarily and probably full of everything. It would look like Mars. Not exactly like Mars, it would be larger, and it would still have an atmosphere, though a thinner one than it has today, and it would still have its magnetic field providing some protection from the solar wind. But in terms of the immediate impression, the color of it, the dryness of it, the absence of blue, the vast exposed plains of rock and dust, the silence, it would resemble, in all the ways that matter visually and climatically, the planet next door. The one that may have gone through something like this already long ago in its own history. Mars, in the current understanding of planetary science, was probably once wet. There are ancient river valleys carved into its surface that could only have been made by flowing water. There are mineral deposits that form only in the presence of water. The evidence for an early Mars with liquid water on its surface, possibly even with oceans in its earliest period, is substantial and growing. And then, for reasons that are still being understood, Mars lost it. The atmosphere thinned. The water escaped to space, or froze at the poles, or was absorbed into the rock. And what remained is what we see today, that beautiful, desolate, completely dry red world. If Mars once had oceans, then Mars knows something that Earth is only now learning. Mars is not a cautionary tale exactly, because the processes that dried it out were different in their details from what we've been imagining for Earth. But it is a demonstration. A proof that a rocky planet in a habitable zone can lose its water. That the ocean is not permanent. That blue planets don't stay blue forever. Earth, in this final stage, would have joined a category that Mars already occupies. Former ocean world. Past tense. Once wet, now dry. The transformation is complete. And the evidence would still be there. This is one of the most quietly remarkable things about geology. The way the past persists in the present, written in rock and mineral and the shapes of landforms, legible to anyone who knows how to read it. Mars has its ancient river valleys, its mineral deposits, its evidence of long-vanished water, still visible on its surface billions of years after the water left. Earth, in its final dry state, would have its own record. The shorelines would still be there. Not the last shorelines, those would have migrated and shifted too many times to leave a clean record. But the ancient ones, the ones carved into cliff faces and canyon walls in the distant past, when the ocean was full and the waterline was stable enough in a given place for long enough to cut a visible mark. Wave-cut platforms, the flat benches that waves carve at the base of cliffs over thousands of years. Fossil beaches, layers of rounded, water-worn pebbles embedded in rock, preserved in exactly the position they occupied when the sea covered them. The chemical signatures of salt water in the rock, the biological signatures of marine organisms in the fossil record, the physical shapes that only water makes when it works on stone over a long enough time. All of it still there, still readable, still proving to anyone who looked what this planet had once been. The fossils in the dried sediment would tell the same story. The preserved shells of marine organisms, the calcium carbonate remains of creatures that had lived in the full ocean and died there and slowly been incorporated into the record. Ammonites and brachiopods and the tiny shells of foraminifera, the microscopic marine organisms whose accumulated remains make up vast thicknesses of limestone. All of them preserved in the rock of the former ocean floor, their presence an unambiguous testimony. There was an ocean here. These things lived in it. This planet was once blue. The maps would be there too in whatever archives survived. The maps of the old Earth, the ones showing the ocean as it had been, full and vast, covering most of the planet's surface. The nautical charts and the oceanographic surveys and the satellite imagery of a blue world. The photographs taken from space in the early days of spaceflight, showing a planet so dominated by water that the land almost seemed incidental. Those images, if they survived, would be among the most extraordinary documents in the archive of the planet's history. Not because they showed something imaginary or mythological, but because they showed something real, something that had genuinely existed for a genuinely enormous span of time and was now gone. And there is something to sit with in that. Something that goes beyond the geological and the scientific and the merely factual, into something that feels more personal, more human. Because the ocean was not just water. It was not just a feature of the planet's surface, not just a component of the climate system, not just a habitat for marine life. It was the origin of life itself, the environment in which the first living molecules assembled themselves from chemistry, in which the first cells formed, in which evolution began its long and extraordinary experiment. Every living thing on Earth is descended from something that lived in the ocean. Every cell in every body on Earth carries, somewhere in its chemistry, the memory of salt water. The ocean was home in the deepest sense. Home to everything that has ever lived on this planet, going back to the very beginning. And its disappearance would be not just an environmental event, not just a climate catastrophe, not just a geological transformation. It would be the ending of something that predated everything else. The closing of the chapter that all other chapters had grown from. In the silence of the final dry Earth, under a sky full of stars that burned sharp and unwavering in the thin, clear air, over the vast and empty basins where the water used to be, what would be left would be the planet itself, still turning, still orbiting the sun. Still ancient and enormous and full of its own kind of beauty, the severe and mineral beauty of a world stripped to its essentials. Rock and dust and the long memory of what had been. The Earth had been blue. For billions of years it had been the blue planet, the one with the ocean, the one with the clouds, the one that glowed with the particular color of deep water seen from space. It has been alive in a way that no other world we have ever found has been alive, teeming with complexity and variety and the constant, restless activity of biology working on every surface and in every depth. And all of it. Every coral reef, every kelp forest, Every whale song traveling across a dark ocean, every storm that built over warm water, every river that ran to the sea, every tide that rose and fell on every shore in the world, every sunset reflected in every wave, every drop of rain on every face. All of it had come from the water. All of it had been made possible by the ocean's presence, by its chemistry and its warmth and its motion and its depth. The fossils would remember. The maps would remember. The ancient shorelines cut into the rock would be remembered. And somewhere, deep in the geology of the planet itself, in the salt deposits and the limestone beds and the chemical signatures locked in ancient rock, the ocean would persist in the only way that things ultimately persist, as evidence, as proof, as the mark left by something immense that passed through and is gone. The blue planet remembering the blue, in the deep silence of a world that was once, and for so long, mostly water. And that is where our story ends, not with a dramatic final wave, but with the quiet and the rock and the stars, and the long, patient memory of a planet that was once something extraordinary. Sleep well.